Good to go.
Okay. Thank you. Can you still see my screen? Perfect. Okay, good morning, everyone. Thank you for joining us. My name is Emily H. with Geosyntec Consultants. I'm joined today by Hannah Carpenter, also from Geosyntec. And today we are going to be presenting the last in a training series for 2025 of wastewater operator certification. This one is on solids handling processes. For the remainder of the presentation, I will be turning off my camera. Okay. So today we've got 4 fun hours of all things solids handling. We're going to start with some regulatory framework. We'll give an overview of solids handling processes, including everything from clarifiers all the way through solids handling and disposal. We'll also cover a couple of auxiliary topics, including sludge pumping and building classification and ventilation. We have a couple breaks built in, so we'll take our first break around 9:15, though we may move a little faster than what's shown on the agenda. So first, I'd like to give some introductions. Thank you to a couple people at Geosyntec that have worked with 8EQ on past trainings. You might have seen some of these faces before. And then a big thanks to Dennis Froelich and Rana Malia over at 8EQ for making this training possible. This is a QR code. You can scan it now, or it will also show up at the end of the presentation. But this QR code is used to provide feedback. So please make use of this. Things that you liked, things that you didn't necessarily like or could be improved upon. We do take a look at this and take your comments into account. All right, so first we're going to start off with a regulatory framework around biosolids. So first off, kind of why should you take this training and why do we use biosolids at all is it's a great question. So Arizona is very dry. It's a desert, as you can see from this image. Most of Arizona is classified as a hot or a semi-arid desert. And biosolids provide much needed water and nutrients to soils to supplement agricultural practices in Arizona. One key thing to note is incineration of biosolids is not allowed in Arizona. So there are several land use application disposals methods, including landfills, but incineration is not allowed. So we need to find something to do with all of these biosolids. Next question is, what counts as biosolids? So the exact definition is written into the state legislature. So it's defined as sewage sludge, including exceptional quality biosolids that is used or applied to land for beneficial properties of the material, such as a soil amendment, a conditioner, or fertilizer. So as that definition said, biosolids are sewage sludge, and sewage sludge has some stuff in it that we don't want to apply to our land or have people touching as they're applying to land. So that includes several pathogens of concern. We've got Helmholtz eggs, protozoan cysts, bacteria, including fecal coliform, E. coli, and Salmonella, and several viruses. And these are key pathogens that you need to prove are reduced throughout your biosolids treatment process. So several ways that we get rid of these pathogens are called biosolid stabilization. And stabilization is when you reduce the biodegradable fraction of biosolids to reduce putrefaction, which means, rotting, and reduce pathogen concentration. So there are 3 methods of stabilization. You have biological, chemical, and thermal. So biological processes include aerobic or anaerobic digestion. If you're going the biological route only, there are restricted agricultural uses, so you can only use it to condition or fertilize the soil. It would require further disinfection for unrestricted agricultural use. For chemical stabilization, that's mainly alkaline stabilization or the application of lime. And if you go the chemical route, you can dispose of your biosolids via agricultural uses or as a landfill covering. And then thermal processes include composting or thermal drying. And thermal stabilization has the benefit of having a high nitrogen content and completely unrestricted agricultural uses because you're, if you follow the process correctly, you will be destroying all of the pathogens. So there are also 3 types of biosolids, all covered under EPA Part 503 Biosolids Rule. You have Class B, Class A, and exceptional quality. And these kind of nest together so that Class A covers, Class B treatment, and exceptional quality covers Class A and Class B. So for Class B, your main goal is you are treating to reduce pathogens and reduce vector attraction, so removing that biodegradable substance. Class B biosolids can be used for agricultural application, but there are some restrictions on human exposure because you don't have the required pathogen reduction. And if using for agricultural application, there are limits to grazing animals and crop harvesting exposure, again, because of that pathogen load. Class A is Class B, but more so treated. So it covers all Class B treatment plus your pathogens are reduced 95 to 99%. And Class A biosolids have more unrestricted use. So you can use it for agriculture application and parks. So people where places where people are going to be exposed more often. And then you have this kind of highest tier of biosolids, exceptional quality, EQ. All Class A pathogens are eliminated. And this is approved for use for unrestricted human contact, landscaping, and gardens.
And Emily, sorry, it looks
Yep.
like we've got a raised hand. I didn't know. Alberto, do you have a question?
Yes, please. Yes, I forgot to ask. I just started talking. If you have a question, feel free to put it in the chat and we can answer. I believe participants' mics are turned off, so you might not be able to ask a question with your audio. Alberto, did you want to put a Q&A into the chat?
I can keep an eye on it, Emily, and let you know if
Okay.
a question comes through. Thanks.
All right, that sounds good. Thank you for letting me know, Hannah.
Cool.
Okay, so moving on to what is actually contained in the EPA Part 503 Biosolids Rule. This is where you will find um, all of the processes that are required. They have different time, temperature requirements. We'll be getting into these in more detail later, but I wanted to present it here in the beginning. We'll be revisiting it first in aerobic and anaerobic treatments, and then more so at the end. Okay, so we've talked about what biosolids are, but what does not count as biosolids. So exclusions include any hazardous waste, any solids that include high PCB concentrations, so that counts as anything over 50 milligrams per kilogram. Grit or screening, so that is important distinction. So at the headworks of your wastewater treatment facility, the grit and screenings that you get off do not count as biosolids. They need to be disposed of separately. Water treatment solids do not count. Industrial wastewater sludge, you don't know necessarily what's in there. And so that also applies to combined industrial and commercial wastewater sludge. Then anything else that kind of is classified as a special waste. Well, sorry, the formatting on this one got messed up a little bit. So this is a graph that was provided by Julia Rowe over at ADEQ. So thank you to her. This graph shows biosolids fate in 2023. So for biosolids applied in Arizona, what you can't really see on that top left is the land application of biosolids that were sourced from Arizona. So that biggest green portion is a 41%. So 41% of all biosolids applied in Arizona are sourced from Arizona. And that next largest chunk, the kind of darker blue in the bottom right, that is biosolids that are sourced from California, and that is 27%. And the main takeaway from this graph is the fact that Arizona is generating a lot of its own biosolids, but it does have ways to supplement biosolids used from California. And then in 2023, Arizona used a lot of biosolids. So approximately 110 million dry metric tons of solids were generated in Arizona. So that accounts for that, 41% that were land applied. And also there are more biosolids being generated in Arizona that are being used in the state than are being brought from out of state, which is the trend that we want to see continue. And the biggest users are Yuma County and Maricopa County. Okay, so we've talked about what biosolids are, some of the classifications. Now we're going to talk about biosolids programs specifically in Arizona. So if you are a biosolids generator, you need to apply for a biosolids general permit. And entities covered under this include private and public wastewater treatment plants and any other entities that are not covered under an Arizona PDES permit. And if you want to land apply biosolids, you need to register for the biosolids land application registration. And that includes facilities that do land application or they do reclamation, also composting sites. This also includes biosolids processing facilities. And the purpose of this program is to make sure that pathogen reduction is met, vector attraction reduction is met, and that the pollution levels in the biosolids are within limits. So Arizona has this really neat biosolids application app where it shows the quantity of biosolids applied every year starting in 2021, which is when the app was released. As you can see, there are several purple circles on this app. So that acts as sort of a heat map layer that represents the quantity of biosolids applied. So the darker purple circles have more biosolids applied. This application will show you registered fields, the dry metric tons of biosolids, and provide other county-wide info. So if you apply biosolids to your land and you don't have this app, highly recommend downloading this. All right, so it is very important to follow all regulations for biosolids. So just like Arizona has the app that you can see where you're applying biosolids, there's a similar and required federal reporting from the EPA. It's the e-reporting tool, it's the NET. That is where you will submit your annual biosolids reporting requirements. And there are also several state regulations that cover the disposal, use, and transportation of biosolids. So I put the exact House bills up here if you would like to read further. Okay, Hannah, any questions on that?
Nothing so far.
All right, sounds good. Okay, so now we'll continue to solids handling process overview. This is a wastewater treatment plant, or a very high-level overview of them. And today we are going to be talking about the processes that generate solids. So solids are removed in several areas of the wastewater treatment plant. Today we'll be talking about primary, secondary clarifiers, and the two thickening and handling processes down below. All right, so in your lab measurements, you have solids, and we have several constituents of solids. We have TSS, suspended solids, we have dissolved solids, and then we have both volatile and inert. So the fractions that we are most concerned about when we talk about solids and biosolids handling is suspended solids and volatile solids. So volatile solids are going to be more applicable for anaerobic digestion. And then suspended solids is going to be the bulk of what is settling out of your processes. So in general, very high level, we have raw wastewater that comes into our treatment plant. You have a series of liquid solid separation steps. We're going to be taking those solids, we're going to be thickening them, handling them in slightly different ways, really to concentrate the amount of solids, reduce the amount of liquid. And then we'll go to a final treatment step for stabilization, and then your final disposal method, if that's land application or landfilling. Okay, this is a overview of a activated sludge wastewater treatment plant. So we'll be using this to kind of track solids and the relative percent of solids as it moves through your process. So as I mentioned at the beginning, grit and screenings do not count towards biosolids. So grit and screenings removes, larger solids, sticks, rags, rocks. These are handled separately. They do not go to the biosolids process. So your wastewater influent is coming in at about 0.25% solids. Your first step is the primary clarifier. So this is to remove settleable solids. And the solids that come out from there are at about 1 to 6% solids, depending on your process. Your aeration basin, we're going to be doing some nutrient transformation via biological treatment. Any carryover from that is moving to the secondary clarifier, which can include biomass carryover and other settleable solids. And so you have your WAS, your waste activated sludge, that's removed from your secondary clarifier treatment tray. And that's at about 1 to 4%. Next, you have your thickened sludge. So, your RAS is sent back to the aeration basin, but your WAS is sent to a thickener where it is thickened via a number of processes. The blending tank can be optional, where we mix a primary clarifier with a thickened sludge. The liquid that is removed from your thickening process is sent back to the head of the wastewater treatment plant. A blending tank is useful for being used for flow equalization. So you can both homogenize your sludge and protect your other processes from flow variations. An anaerobic digester, in this case, consumes organics. It also does some pathogen removal, which is, we'll get more into that when we talk about Class B biosolids. Biogas capture is also a potential for an anaerobic digester. And then your sort of final step is solids dewatering. And this is where we are removing a lot of the water, and hopefully we're getting about 15 to 40% solids concentration. So in a number of steps in these processes, you have the option for chemical addition of different kinds. So we would add chemicals to sort of increase the buoyancy differential of solids, either make them lighter if we're going to be using dissolved air flotation, or making them heavier. It's just really to help increase the efficiency of solid separation. It can also be used to intensify thickening and dewatering processes. So instead of making a unit, like getting a bigger thickener, we can add chemicals and just really sort of increase the efficiency of a smaller unit that we have. So we can decrease the equipment size. It can also increase your throughput of sludge handling, and some chemicals, including ferric and lime, can be used to control odors and scaling. So some commonly used chemicals include ferric chloride, lime for that alkaline treatment. Several polymers can be used for coagulants and flocculants, and then potassium permanganate can also be used for odors. Several common locations for chemical addition include a lot of inlets, so inlet to your clarification, your thickening processes, digestion, dewatering, and then also post-dewatering stabilization if you're going to be using lime stabilization. So of your coagulants and flocculants, you have several types. So some of them are oxidizing agents that are used to reduce odors, also used to reduce polymer dosing. And these include potassium permanganate and ferric sulfate and chloride. Of your coagulants, the most common ones can include aluminum sulfate and aluminum chloride. And for flocculants, you have polyacrylamide and polyaluminum chloride as some common ones. Okay, do we have any questions on solids overview? No?
No questions at the moment.
Okay.
If something comes through in the chat, I'll let you know.
Okay, sounds good.
Great.
All right, next we're going to move on to primary and secondary clarification. So, primary and secondary clarifiers work through a process called sedimentation, and that really is just when heavier particles fall out of solution because they are heavier than water and we remove them from the bottom. The fancy specific term is that their specific gravity of the solids is greater than 1 because 1 is the specific gravity of water. So clarifier functions, they do several things. So they can do flocculation. Flocculation is defined as the aggregation of dispersed particles to form a flock. Clarification, which is when you separate solids and liquid fractions to produce a clarifier effluent. Clarifiers provide the maximum removal of TSS and BOD/COD. They can also provide some thickening, so they produce a thickened sludge stream out of the underdrain. And they can also provide some storage, so can give you a little bit of a buffer for accumulation of solids, particularly during storm events. So a little bit of an overview of clarifiers. You have your influent from the grit and screen system that is coming in. Again, that's going to be about 0.25%. And then depending on the size and operational parameters of your clarifier, the solids that you get from that underdrain should be anywhere between 1 to 6%. There's a separate scum line that can be sent to solids handling. And the target TSS removal that we're looking from a primary clarifier is 50 to 75%, and BOD removal from 25 to 40%. After that, it moves on to secondary clarification, again from a activated sludge wastewater treatment plant. So there are 2 waste streams coming out of the secondary clarifier, the WAS or the WAST activated sludge, and then the RAS or the return activated sludge. As the name implies, return activated sludge is sent back to the aeration tank to maintain that biomass balance, and then waste activated sludge is wasted and sent to solids processing. And that you waste sludge to maintain a solids retention time. There are a couple parameters that can be used to control your clarifier. These are also relevant to other solids handling processes, but I will just introduce them here. So we have 2 different retention times. We have a hydraulic retention time and a solids retention time, and they are very similar, but we include 2 different definitions. So hydraulic retention time is the amount of time that 1 gallon of water spends in the system. It's important. It's an important parameter, HRT, to ensure that there's enough time, hydraulic retention time, for pollutant degradation. And you control HRT by flow and the size of the basins. Solids retention time is defined as the amount of time that biomass remains in the system. This is more important for biomass growth. So you might have solids retention time might be a more important parameter in digestion than necessarily, your primary clarifier. And it's controlled by the sludge wasting rates. So some other operational parameters for clarifiers include hydraulic loading on the clarifier. So how much water are you loading onto the clarifier? Your tank configuration, if it's circular versus square, the wastewater characteristics, if you have a stronger wastewater or a more dilute wastewater stream after the storm, you might need a little bit longer of a hydraulic retention time, particle characteristics, and temperature of the water. These are a series of kind of visual representations of retention time that I hope make these ideas a little more understandable than just having words on a screen. So for retention time, we have the clock in the middle, and the one up top is a shorter retention time because it has, only about 20 minutes or so. So you have flow coming in, and then you have a smaller flow of sludge going out because it's a shorter retention time. The clarifier on the bottom, you have a longer hydraulic retention time, and so that's giving more time for solids to settle out, and so you have a larger sludge stream coming out the bottom. We also have surface loading rate. So surface loading rate is defined as the flow going into a clarifier divided by the surface area of that clarifier. So if you have this essentially kind of measures the capacity of your clarifier. So if you have a higher flow going into your clarifier, you're going to have a higher flow going out because you're limited by surface area. And you will also have a shorter hydraulic retention time. So you're going to get less sludge coming off the bottom just because you're pushing too much flow through your clarifier. And then the one on the bottom has a smaller surface loading rates. So you have a smaller flow coming in, a smaller flow of effluent coming out, but then a larger volume of sludge coming out the bottom. Okay, surface loading rate. So surface loading rates, solids loading rate. This is more so relevant for your secondary clarifier because as you see on the bottom in that equation, we have a RAS factor. So that's a return activated sludge. And this similarly, if you have a higher solids loading rates going in, so if you have more RAS coming into your clarifier, you're probably going to get more sludge out just because you have more sludge in, more sludge out. One final parameter to mention about secondary clarifiers is the solids wasting rates. This is a lot of equations. We're not going to be doing any examples on it today, but it is here because this shows you sort of the idea behind your system boundaries. So when you're looking at the effectiveness of your removal processes, or if you're trying to evaluate the capacity of your system, you can take a look at your rates, and that is defined around the aeration basin and the secondary clarifier. So you have solids in your influent coming in, and then you have solids in your effluent leaving, both in the secondary effluent, which should be pretty clear, and then your waste activated sludge coming out the bottom. And here is a representation of that, where you have more solids in, and then you'll have more solids out. Do we have any questions on that?
Not seeing any yet, but
Okay.
yeah, and thank you, Mark, for pointing out that the chat was disabled, but it seems to be working now, so appreciate it.
Great, thank you. Thank you for handling that. All right, now we're gonna go over thickening. There are no questions on. Yes,
There's
go ahead.
one question, Emily.
Yes.
Will we be just discussing how these tie in with SRT?
Sorry, what are tying them with SRT? The clarifier design?
I think maybe the wasting rates. I know we will go into a little bit more information, especially in the digestion section about SRT as well. hopefully that'll answer your question. If we didn't, please feel free to add a second.
Yes. Okay, great. Yeah, we will wait until digestion. Yes, but thank you, Mark. Let us know if your question doesn't get answered after
Awesome.
after we're done through that section.
All right. Thank
Okay.
you.
Yeah, thank you. All right, on to thickeners. So, why should we thicken sludge? It has several benefits, including reducing the overall volume of your solids that you have to handle, which then leads to lower CapEx and operational costs. So, briefly, a thickener is you have raw sludge coming in from your primary and secondary clarifiers, and you get a thicker sludge at the bottom, and you get a supernatant up top that is set back to the headworks. And you can add chemicals at the head of these, including any polymers, coagulants, flocculants. You can also add ferric for odor control. So very generally, there are two sort of physical processes that are governing thickening processes and also two dewatering processes as well. You have gravity, which is where things go to the bottom that are heavier. And then a other process is sort of this dynamic force of centrifugal force. So it's the process that's used for centrifuges and other processes that spin. So if you spin something, the heavier particles sort of move to the outside. So a quick overview of different thickening technologies that we will discuss are gravity thickeners, dissolved air flotation, rotary drum thickeners, gravity belt thickeners, and a disc thickener. These are all different ways that separate solids and liquid. Their main differences are the chemical additives, power consumption, their batch versus continuous, and then the level of operator involvement that is required. So the first up is a gravity thickener. A gravity thickener is essentially a clarifier, except we are accepting sludge in instead of wastewater influent. So sludge is fed into the tub. We're using gravity to separate out solids, which are moved to the bottom. Sludge is scraped out the bottom. Gravity thickeners will have a longer retention time with lower solids loading rates. So I guess kind of going back to that SRT question a little bit, if you have lower solids concentration coming in, you're going to need a longer solids retention time to get your sort of target thickened sludge concentration out the bottom. Some operational parameters include detention time, retention time. So too much time can cause the sludge to go septic. If it's just sort of sitting there, you can get, anoxic conditions, which will cause it to break down. Too little time can reduce your sludge capture, and you're not getting your target solids concentration at the bottom. Other operational parameters include polymer dosing. If you're co-thickening primary and secondary sludges, sludge blanket depth. So this can be measured by infrared detector or a sludge judge, which is, if you haven't seen a sludge judge, it's essentially a big ruler with measurements on it, sort of like a yard ruler that you will put down and you can measure how thick your sludge blanket is. And then also you will have to use sludge removal pumps. Most commonly used are positive displacement pumps. Several operational measurements for operators to take and be aware of are your total solids in the feed and thickened sludge. So this is going to be your main method of measuring the effectiveness of your process. Again, that's solids in and solids out. The suspended solids in your supernatant will kind of help you close that mass balance, and also the BOD and the supernatant. The feed flow volume is a parameter that you can change to change the operations of your process. Sludge flow volume, sludge blanket depth are all operational measurements that you will need to take to also measure the efficiency of your process. And then, as we said, temperature in the feed coming in and then the thickened sludge coming out. Some common maintenance for gravity thickeners include checking oil levels in the gears, the drive control limit switches, inspection of skimmer and skimmer wipes, adjust and assemble the drive belts for any motors that are present in the process, and then an annual clean, emptying, and inspection of your thickener. So some pros to gravity thickeners is that they are simple to operate and they're simple to maintain. They have a lower operating cost than DAF or gravity belts. Some cons include odor concerns and scum buildup. So they do take a little bit of a longer time. You can get more odor concerns. Grease can build up and block the lines if you're not getting a lot of flow through them. Again, you can get septic conditions, which can cause odors. Also operationally, there's a little bit of difference because you are just relying on gravity. You can get lower sludge solids percent in your thickened sludge and a higher supernatant solids percent than other thickeners such as a DAF or a gravity belt. And also it has a pretty large footprint. It's just a tank. There's not a lot of mechanical operations going on that are going to improve on gravity. So you do have to have a lot of space available for a gravity thickener. Next up is a dissolved air flotation system, or a DAF. These can be any shapes. This example image down here is essentially kind of a clarifier, but turned on its end. These also come in skid form as well. So the idea behind these is that you are kind of turning gravity on its head. So air is diffused into the bottom. Solid particles adhere to the air bubbles and they float. And so you have your skimmers on top of the water that are removing the solids that are floating to the top. And then you're getting sort of clarified water at the bottom. And then coagulant is also added here to help with solids removal. So some operational parameters for DAS include the air pressure of your bubble diffuser. If you have higher pressure, you will get a sort of a higher through rate of bubbles. So this is something that needs to be fine-tuned because too much bubbles might prevent the solids from really kind of sticking together. A recycle ratio of treated water that you're feeding back into the DAF system, the air to solids ratio. So the air that you're feeding into the DAF versus the solids inlet that you have coming into your DAF. Again, hydraulic retention time or solids retention time, coagulant and flocculant dose, and then the sludge volume index are all operational parameters. Operational measurements that need to be taken daily include air pressure and flow, coagulant dosing and pump operations, flocculant dosing and pump operations. We want to make sure that we're feeding in the correct amount of coagulant and flocculants. With DAF, you need to measure your influent and effluent conditions for fat oils and greases, COD, pH, and TSS. Common maintenance of DAF includes polymer feed hopper and dose pumps maintenance, a washdown of the DAF tank and the sludge hopper, and then the maintenance of the air diffuser system, which include the vacuum pump and compressed air canisters. You'll need to make sure that the canisters are full of air and that you have backups available. So some pros and cons of DAF is that it has a smaller footprint than other thickeners, and it can achieve a higher solids percent than other thickeners. And if you are using, if you have a activated sludge process, DAF has been proven to be the most efficient for suspended growth biological processes. So for those WAS sludges that you might have in your system, it can also be used for sludges containing metal salts. to help with that separation. Some cons to DAF include an increased equipment requirements. So you need an air and a vacuum pump, and you need diffusers, you need those air canisters. The air to solids ratio will greatly influence your performance. So this can be a little tricky to get right. You might need some trials to figure out what is the right ratio for your system. And because of that, it can be difficult to predict performance with bench or pilot testing. So there is kind of a learning curve at the beginning. And if you have a higher SVI, that's going to require a higher polymer dosage, which will increase your operational costs. Okay, moving on, we have a rotary drum thickener. Rotary drum thickener, as the name implies, uses a series of rotating drums. So the drum will rotate. Water is removed via sort of perforations that are in the drum wall. You have a spray bar that will clean the drum and keep those pores open and clean. Solids is retained inside the drum. And again, here you can have the option for adding coagulant upstream to help with solids removal. Some operational parameters include your rotational speed, your sludge feed rates, cleaning frequency, polymer dosing, and feed flow rate and total solids measurements of your influent sludge. Some operational measurements that will need to be taken include the TS of the thickened sludge and the filtrate. So that will help you measure your efficiency of your process and close the mass balance. Drum rotation speed. Too slow of a drum rotation speed can cause the pores to become clogged. Too fast of a rotational speed can potentially not give the water enough time to kind of make it through the solids to drain out. So that reduces your efficiency. And again, your polymer dosing and the age of your polymer as well is an operational measurement that you will need to take. So some pros of rotary drum thickeners include a very high solids recovery rate, about 93 to 98%, which is very efficient. You have options for combined thickening and dewatering if you want to combine it with a belt press on the back end. And these also have a pretty small footprint. Some cons for this is that they require a sludge conditioning system to help sort of with that liquid solid separation. So you will need polymer or other conditioners. And large amounts of polymer can be required for conditioning. And if you add too much polymer, it can impact your flock stability, which can impact the efficiency of your dewatering processes downstream. And another con is that drum thickeners are batch operations. So each batch will need to be conducted anew, and that can lead to lower throughput and more operator involvement. Okay, next up is a gravity belt thickener. Gravity belt thickeners essentially use a circulating belt on a series of rollers up top. So solids are fed in up top. There's a number of plows that kind of help break up the solids so that water will drain down through the bottom. Spray bars, just like in the rotary drum thickener, are used to clean the belt after each pass, and coagulant and polymer is added upstream to help with solid separation. So some operational parameters include polymer agent dosing, your belt speed. If your belt is going too fast, you might not be getting enough time for water to separate out. If it's going too slow, you might be clogging your belt. So there's a little bit of a sweet spot. Belt size and type. And again, the hydraulic loading rate and solids loading rate. Some operational measurements that need to be taken are chemical dosing for your coagulants and flocculants, polymer dosing and age, volume of cake leaving the belts will help you measure the efficiency of your process. And then also that total solids for the feed sludge, cake, and the filtrate will help you close that mass balance and see if you need to make any changes to your belt operations. Some pros to gravity belt thickeners are that they have low staffing requirements. It's a sort of continuous process, and sort of once you get it dialed in for your sludge, it's very easy to let it operate. Simple maintenance. The largest concern is that belt replacement is required periodically. They have quick startup and shutdowns. They're not like centrifuges where you have to give them some time to get going. And there's minimal noise, so they are much quieter than centrifuges as well. Cons is that odors must be managed with ventilation and chemicals. If you do have any variation in your solids feed, that does require increased operator involvement. If you have a high fog content in your solids, that can clog the belt. And belt washing can be very time consuming and require large volumes of water to be handled elsewhere in the process. Next up is a disc thickener. So this is kind of like a rotary drum in principle, it's just a slightly different shape. So a rotating disc uh, rotates around on the inside and it builds up a sludge blanket on one side. And so sludge is pushed out. If you can see in this image, sludge is fed in through the middle here. This disc will kind of go around and around. Because it's tilted, you will get a higher buildup of solids on this side, which creates more pressure for water to drain down. And then you have solids carry over up to this high point and then eventually out to your other processes. And as with the other technologies, this one also is equipped with a spray bar to kind of keep those pores clear. Some operational parameters that you can use to change your performance include your disc rotational speed, very similar to the rotary drum thickener. If you go too fast, you might not get the solid separation that you want. Go too slow, you might reduce your separation efficiency because your pores are getting clogged, you're not cleaning them fast enough. And on that point, the cleaning system operation of that spray bar is a parameter that will affect your performance. Your sludge feed rate, and then also your polymer dosing and age will affect your solid separation efficiency. Some operational measurements that need to be taken are the TS of the sludge fed into the thickener, and then your TS of your cake and your filtrate to help you close that mass balance, and then also your polymer age and dosing. So some pros of rotary disc thickeners are that they have a smaller footprint than a lot of other thickening technologies. The con is that they're a little niche, so they're not as common as other thickeners, and so specific vendors are required, specific training could be required, and any specific operator training is also going to be required. So that takes us through our thickening overview. Do we have any questions?
Give people a minute. Oh, okay. We've got one question from Tim.
Okay.
Any suggestions for efficient removal of sludge from facultative lagoons?
I think we are gonna cover lagoons later. Um, Not off the top of my head. Hannah, do you have anything?
Ah, Tim said, okay, thanks. Yeah, I think we're going to talk a little bit about lagoons in a bit, but I know I've seen some methods, just dredging and then also dewatering of some of the, I guess dredging and dewatering is what I would suggest. But yeah, we'll talk about it a little bit later as well.
Yeah, yeah, that was gonna be, I think those are the two things that we're gonna be discussing.
Awesome.
Yeah. Those are a little harder because, you just have a bunch of sludge in a bed and so it's just kind of normally taking a front loader in there and digging them out. Um, but if
Cool.
that but if there are no other questions, uh, we made it through our first break, so we are ahead of schedule. We have a 5-minute break built in, so it is about 8:53 now. Um, we'll
Let's
just get let's give ourselves 7 minutes. Return at 9.
great.
Okay, thank you, everybody.
Thanks. Okay, just about 9 o'clock. We'll give people another minute or so to come back into the meeting. Nathan, thanks for that information on the lagoon troubleshooting manual. That's great. All right, well, I think we can go ahead and get started. Um, as Emily mentioned, my name is Hannah Carpenter. I also work with Geosyntech. I'll be doing the next section of the training focused on digestion. So we'll be focusing on aerobic and anaerobic treatment. So why digestion? As mentioned earlier, in the digestion is a part of the 40 CFR Part 503 standards for the use or disposal of sewage sludge. This regulation regulates sewage sludge that is applied to land fired in a sewage sludge incinerator or placed on a surface disposal site. This was created as part of the Clean Air Act. So EPA Part 503 focuses on vector attraction reduction requirements and meets the EPA requirements to process process to further reduce pathogens or the process to significantly reduce pathogens. And this focuses on total and volatile solids reduction. So vector attraction reduction requirements ultimately treat pathogens. We've all heard of different types of pathogens, which are organisms capable of causing a disease to a host, such as bacteria, viruses, or parasites. These treatment systems provide a less effective environment for microbial growth. Ultimately, it inhibits growth to stop further production and ultimately reduces the number of pathogens. As you can see in the table below, we measure the effects of treatment of pathogens based on log removal. So in this section, we have anaerobic digestion, aerobic digestion, and then later on in the course, we'll be talking about composting, air drying, and lime stabilization. But you can see the different log removals for each of the different types of pathogen there in the table. And for example, if you're not familiar, 1 log reduction is a 90% reduction, and a 4 log reduction is up to 99.99% reduction. So the EPA Part 503 biosolids rule came up with 2 classifications for solids treatment, Class A and Class B. As you can see here, there's a lot of different alternatives to treating sludge, but we're going to be focusing on the ones that are more detailed into digestion. So firstly, under Class A, we have Alternative 1, which is thermally treated sewage sludge, and Alternative 5, which is the use of a PFRP, or the process to further reduce pathogens. And then in Class B, we have Alternative 2, which is the use of a process to significantly reduce pathogens, or a PSRP. I'll explain in more detail a little bit about each of these. So for Class A, Alternative 1, the thermally treated sewage sludge, this alternative is used when the pathogen reduction process relies on a specific time temperature regime. And as you can see in the table, there's 4 regimes. We typically don't see greater than or equal to 7% solids going into a digester, so those don't typically apply, but the less than 7% solids applications do. So when sludge is heated for more than 15 seconds, but less than 30 minutes, or heated greater than 30 minutes at 50 degrees C. There are different equations for each of these different time temperature regimes in the EPA rule book if you want to look into them, but just wanted to give you an overview today. So the second Class A alternative is Alternative 5, the use of a process to further reduce pathogens. There are two that apply to our digestion. First one being thermophilic aerobic digestion, and the second one being heat treatment. So heat treatment is pretty much what it sounds like. You heat liquid sewage sludge up to a temperature of 356 degrees Fahrenheit for 30 minutes or more. This is not super typical in the United States, but seen more over in Europe. Additionally, thermophilic aerobic digestion is when sludge is agitated with air or oxygen. So typically you have a blower with diffusers, and it maintains the aerobic conditions for the mean cell residence time to reach 10 days at 55 degrees C or 131 degrees F, or up to 140 degrees F. Next, the Class B Alternative 2, use of a process to significantly reduce pathogens. This is pretty typical in the United States and probably where most of our wastewater treatment plants land. First application, obviously aerobic digestion, and then second being anaerobic digestion. So talking a little bit more into aerobic digestion, like I mentioned before, the sludge is treated with air or oxygen to maintain the aerobic conditions for a specific solids retention time at a specific temperature. Because of the large retention time required, we typically only see these at small wastewater treatment plants, less than 5 MGD, just given how much tank you need for this application. And so anaerobic digestion is, like I mentioned before, sewage sludge is treated in the absence of air for a specific solids retention time at a specific temperature. Given that you are heating the sludge a little bit higher in this application, you have a lower retention time. So some key parameters of digestion. Solids retention time, hydraulic retention time, volatile solids reduction, temperature, pressure, specifically with anaerobic digestion, and then the different types of microorganisms that you see throughout the processes. I'll go into further detail in the following slides about each of these different parameters. So solids retention time, I know Emily talked about this a little bit earlier. It's the average time that the solids spend in the digester. Pretty much controls the concentration of bacteria in the digester and varies based on your temperature classification, and the overall classification of your effluent solids, whether you're Class A or Class B. And I'm bringing up this fun graphic that Emily had earlier, another representation of hydraulic retention time, because this does also apply in digestion. Basically, flow in, flow out. If you have a higher hydraulic retention time, you'll have less flow going out. And then another very important parameter in digestion is the volatile solids reduction. So the volatile solids are the portion of the total solids representing the organic matter within the digester that can be volatilized, or so this refers to the process of breaking down your organic components in your digester. The equation that you see at the bottom is you end up with a percentage of based on your mass in of volatile solids and your mass out of volatile solids. The typical volatile solids reduction for anaerobic digestion is 45 to 65%, whereas aerobic is 38 to 50. And temperature. So temperature is very important in digestion, both aerobic and anaerobic. It influences the metabolic activity of the microbial population. In digestion, there are three temperature ranges, so psychrophilic, mesophilic, and thermophilic. Mesophilic is the most common here in the United States. It's used for Class B solids. And then if your temperature ends up going outside of the microbial preferred range, you could have impacts on gas transfer rates, rates of digestion, your volatile solids destruction, like we were just talking about, and overall bacteria is very sensitive to temperature ranges or changes. So once you've got it set up, it's very important to keep it in the same range. Lastly, microbial colonies. So the species structure determines the metabolic pathways that happen in the digestion system. So as we can see here, you could have different nitrifiers, denitrifiers, phosphate and glycogen accumulating bacteria, filamentous bacteria, depending on the different parameters that we just talked about before, that could affect the type of treatment. And lastly, as an overview, some normal inputs to digestion, kind of what Emily was talking about a little bit earlier, and with the different sludge streams, we have waste activated sludge, primary sludge. We can have combinations of primary and secondary sludge blends. And then you can also include food waste or fats, oils, and greases into your digestion process to improve treatment. So I'll pause there to see if anybody has any questions on the overview, and then we can get in a little bit more detailed on each of the different types of digestion.
No questions yet, but maybe we can give people a second to type in something in.
Okay, cool.
Okay, it looks like we're good to go.
Okay, great. Thank you. All right, so first off is aerobic digestion. So aerobic digestion is typically for treatment of the following combinations of sludge. So WAS only, a mixture of WAS or trickling filter sludge and primary sludge, and then WAS from an extended aeration process. Like I mentioned earlier, the typical plant size is less than 5 mgd, just given how much the higher retention time causes you to need a larger tank. And aerobic digestion typically produces Class B biosolids at the listed time and temperature range below. So aerobic digestion is really similar to the activated sludge process. Basically, microorganisms consume their own protoplasm to obtain energy for cell maintenance. So they kind of are eating themselves. So I thought this graphic was fun, just to show you exactly what the protoplasm is in the cells. So you can see it's a combination of the nucleus, nucleolus, and the cytoplasm. And next, I'm going to go through the different steps of aerobic digestion. So first step is biomass destruction. So like I was just talking about, basically in your digester, your food supply is depleted, so organisms consume their own protoplasm. So you're introducing air into your process, so you're oxidizing your protoplasm with ox oxygen, and then you end up with carbon dioxide, water, and ammonium bicarbonate. Because of this, you do end up raising the pH in this step. Next step is nitrification, which is the release of ammonia. So ammonia is produced in this. It's you need to reduce ammonia because ammonia causes odors and it's toxic to the microorganisms. With this step, you end up with a pH decrease, but it's mitigated. And then aerobic, the last overall equation with complete nitrification is shown here. And again, you don't need to memorize these chemical equations. I'm just putting this on here for visual representation, but this is the total equation with complete nitrification, which is the combination of biomass destruction and nitrification. The pH is raised by HNO3, and it's toxic to microorganisms, so you need to make sure that you're monitoring that through the process. Most aerobic digesters stop at nitrification, but there is a potential that it could go on to the next step, which is denitrification. This would be the final biological process. It is an anaerobic process, which is basically you remove nitric acid, which is toxic to the biomass. So the equation is listed below. And on finally, if you do go through complete nitrification, denitrification, you end up with CO2, nitrogen, and water. The equation's listed here. All right, so volatile solids reduction. As I mentioned before, in aerobic digestion, you're able to get 35 to 50% reduction in your volatile solids. The CFR Part 503 requires that your specific oxygen uptake rate is a minimum of 38% or less than 1.5 milligrams O2 per hour per gram of total sludge solids at 20 degrees C. And so the specific oxygen uptake rate is pretty important when you're looking at your aerobic digestion. In order to measure this, you use a diometer and a BOD bottle. Basically, it measures how much oxygen is consumed over a short period of time. The bacteria uses more oxygen when they're growing and dividing so that you would have a higher sour. The lower rate could mean the introduction of a solvent or other influent that inhibits the microorganisms from living. So sour testing confirms microbe inhibition or toxicity. So the inhibition would be temporary, short-term, or long-term loss on enzymatic activity, and toxicity would be permanent loss of activity or damage to the cellular structure. If your ideal operating sour is not reached, you could have elevated BOD, high ammonia, and high TSS. So overall, aerobic digestion, some pros are you have lower BOD concentrations in side streams, less odor. It's a pretty simple technology, basically just a tank with a blower. And lower capital costs for smaller facilities, and additionally, no risk of explosions because you're not creating a biogas. Some of the cons are due to the amount of oxygen that you're putting into your tanks. You do have a higher power cost. You're not producing methane for potential energy capture. Typically, aerobic digested sludge has poor dewatering characteristics, so you might see a lower percent solids at the end of your process. And it is affected significantly by temperature. So the process itself does not include any sort of heat introduction into the system. So your external temperature really affects the process. So probably not the best for a colder climate. And then the process does consume alkalinity, and like I mentioned before, longer retention times. So there are a couple of types of aerobic digestion. I'll go into a little bit of detail of each of these. So your conventional aerobic digestion is pretty much as is shown on the screen. You've got a tank, you've got air coming into the system, and then you have your supernatant line coming off, and then your waste sludge draw off from the bottom of the tank. Conventional aerobic digestion should be able to be batch or continuous flow, depending on your process. Probably most typically is continuous. Like I mentioned earlier, temperature has a lot of effect on the process, so you should be able to operate at ambient temperatures. That'll be taken into account when through the design, but they're usually open air tanks. And then the SRT, like we mentioned before, between 40 and 60 days, but at the two different temperatures listed below. Another type of aerobic digestion is high purity oxygen aerobic digestion. So this is basically instead of introducing air, you introduce pure oxygen into the system. So it's a little bit more expensive, but it is better in cold weather climates because Um, it's less sensitive to changes in the ambient air temperatures. Um, you you do get a little bit of an increase in your volatile solids destruction, just given that you are implementing pure air into the system, or pure oxygen, apologies, into the system. But this is a less common application. The final application is autothermal thermophilic aerobic digestion. You can have this with both conventional or high purity oxygen aerobic digestion. The feed sludge in this process is pre-thickened to about 3 to 5% optimal. So usually we'll see about 1 to 4% sludge going into a digester, but this would be a little bit thicker. This would be operated at thermophilic conditions, so there would be a heating element to it. And because of that, there is a shorter hydraulic retention time. But again, this is not super common. All right. And so with aerobic digestion, we have different types of mixing. We'll have mechanical aerators. So that would sometimes look like a big aerator in the middle of a tank, or there are also diffused air mixing. So like you can see in the picture on the left with diffusers at the bottom of your tank. These could be the disc or tube, but with mechanical aerators, routine maintenance, the motors, diffuser maintenance, you would need to get in there and clean and replace your diffusers as they wear and tear. So key operating considerations for aerobic digestion are, like I mentioned earlier, temperature, pH, because there are pH adjustments as it goes through the aerobic process. Additionally, foam could be an issue, and odor control, as these tanks are typically open top, exposed to the elements. Um, So a few more operational considerations, like I mentioned, pH, you can drop down to a value of as low as 5.5 at certain points in the process. So definitely something that needs to be monitored throughout. Additionally, you can have an increased presence of nitrate, and then filamentous growth could occur. And filamentous growth causes the instability in the bacteria present. Additionally, the dissolved oxygen, so how much oxygen you're actually putting into the system, you need to make sure you're providing with enough oxygen so that the process can go through the entirety of the steps of aerobic digestion. And additionally, the feed solids concentration may affect mixing and aeration, and it varies based on the aerobic treatment type. All right. Any questions on aerobic digestion?
Looks like no questions yet, but maybe we'll give it a minute.
Okay, sounds good.
Okay, looks like nothing has come through, so anaerobic
Okay.
digestion.
All right, cool. So on to anaerobic digestion. So anaerobic digestion is treatment without the presence of oxygen. So it converts organic compounds into methane and carbon dioxide to create biogas. You can produce Class A or Class B biosolids, and you can recover energy in the form of biogas. And it does produce a soil amendment product based on the classification. So this is a fun EPA graphic of anaerobic digestion, kind of showing all of the different inputs that can be added into anaerobic digestion. So we'll mainly focus on wastewater biosolids, but you can add manure, food waste, and other organics into the system. And then from the anaerobic digestion process, you produce biogas. Biogas can be used as electricity, heat, vehicle fuel, and in some locations it can be processed and used as renewable natural gas. And then your sludge coming out of the digestion process can be used for fertilizer, land application, based on the different classification. So anaerobic digestion goes through 4 different steps. Shown here, kind of the purpley color are the different steps that it goes through. So hydrolysis, acetogenesis, and methanogenesis. And it kind of shows you, I'll go into this in a little bit more detail, but how things are broken down. So the first step of the process is hydrolysis. So kind of taking the super complex organic molecules, long chain, in the beginning of your process, breaking them down into simpler, more soluble molecules, sugars, amino acids, fatty acids. And then acetogenesis is those smaller chains are broken down even further into short chain volatile fatty acids. And then from there, acetogenesis, the VFAs are broken down even further into acetic acid, hydrogen, and carbon dioxide. And then final step is methanogenesis, is where your acetic acid, hydrogen, and carbon dioxide are broken down into producing methane and water. And this is where you produce biogas. All right. So, anaerobic digestion and alkalinity. So higher alkalinity in your system prevents pH changes, and therefore prevents acidification as it goes through. So this is a parameter that you want to monitor. And then, so the anaerobic digestion process can be either single stage or two stage. Single stage is probably the most common, but two stages is also seen. So single stage, high rate digestion, you can see in the top image here on the right, it's basically one tank. And then the two-stage digestion, you have two tanks. So in the first tank, it's mixed, and then the second tank, it's a little bit more stratified. And I'll talk about that a little bit more. So single stage high rate digestion, you have your heating component, you have uniform feeding, so it's either continuous or on a timed cycle. And with that, it is continuously mixed within the tank. So no stratification occurs. And then typically you have a fixed roof or a floating cover on the top of the tank to maintain those anaerobic digestion. And so two-stage digestion, which is the other option that we were looking at on the other screen, is the first tank is used for those first 2 steps in anaerobic digestion, the hydrolysis and acetogenesis. That tank is heated and mixed, so very identical to the single tank option, but the second tank is used for acetogenesis and methanogenesis. Within that tank, you usually have some stratification, so you'll have a supernatant at the top, and then your sludge would come out of the bottom. This is not, like I mentioned, not super common today, just given the supernatant may have high concentrations of TSS, and when you're trying to put that back into your treatment process, it could cause spikes. So, um, moving on to the 2 tank types. So as you can see, anaerobic digestion can either use a conventional tank, which is basically a normal tank with a cover, or it can be egg-shaped. The egg-shaped digesters are not as common in the United States, but seen more in Europe. And the egg-shaped digesters are more commonly seen as in the thermophilic anaerobic digestion. So this is an equation, kind of complicated equation. Don't need to memorize this, but just wanted to kind of put this on the screen to show you that there is, if you're curious, there's a way to calculate methane gas production from your anaerobic digester based on your BCOD and the influent and the effluent, and then based on the mass of cell tissue produced per day. So again, complicated. If you get curious, it's here for your use. So within anaerobic digestion, there are multiple different types of mixers that you can use. Um, First off, we've got gas injection. So with this one, as you can see in the picture, we've got gas being collected at the top of the tank, going up on a line up into a gas compressor and then re-released into the tank through an eductor tube. Basically forces pressure and the gas mixes the sludge within the tank. Second is mechanical stirring. So this is just stirring your tank with mixers or turbines, usually rotating impeller. So in these two pictures, we're showing a mixer at the top center of the tank, but you can also have mixers on the sides of the tank as well. And then lastly, mechanical pumping. So two different types of mechanical pumping, one being draft tubes. Draft tubes have propeller type pumps inside the digester, so nothing is on the external side. Or so the second option is external pumps with basically you've got a pump sitting outside of a tank. You've got piping that'll go back into the tank with nozzles that will shoot the sludge back into the tank. Sometimes they'll have different configurations so that you can pull sludge from the bottom of a digester and have it go back into the tank at the top and vice versa, so you can allow for vertical mixing. Next, so with anaerobic digestion, we do need to heat the digesters. So as you can see from this graphic, a typical process is we'll pull sludge from the primary digester into a pump. Sometimes the influent sludge is added directly after the pump from the digester. And then from there, the sludge will go into a heat exchanger where it will it'll be heated and then sent back to the digester. And the sludge is heated using usually a boiler with pretty hot water. And so you'll have a hot water loop as well as a sludge loop. With the heat exchangers, two typical types of heat exchangers are spiral and tube and tube. The image on the left on the bottom is a typical tube and tube heat exchanger, and then on the right we've got a spiral heat exchanger. With the tube and tube heat exchanger, you can kind of see there's basically a tube of sludge that's pumped through the system, and the tube of sludge is inside of another pipe of water. So the water on the outside heats the sludge on the inside and it's pumped through the system. Whereas the spiral heat exchanger, you've got two different, I guess, loops, chambers of sludge. The sludge and the hot water pass each other as they go through the chambers, and that's how the sludge is heated. Some parameters to watch out for with boilers and heat exchangers. Temperature monitoring on both your sludge and your boiler hot water loops is very critical for operations. If your temperature in your water is too high in comparison to the temperature of your sludge, you have the potential to bake the sludge on the inside of the pipes, which is really hard to clean off and definitely not recommended. And then also on the opposite end, if your temperature is too low, you could inhibit digestion because your sludge going back into the digester isn't hot enough. Both types of heat exchangers and the boilers require routine cleaning. So pretty much you can remove the ends of the heat exchanger caps and get in there to clean the tubes. And then boilers, you can use a chemical agent to clean and make sure you don't have any scaling. In addition, the boilers can use biogas for power, so that's another consideration to make for a more sustainable operation. In addition to that, you could also have cogeneration. So cogeneration generates electricity from digester biogas. So you'll probably hear it also known as CHP, combined heat and power. With cogeneration, you have microturbines or combustion engines. And this really depends on the amount of biogas that's produced at your plant, if cogeneration makes sense. Smaller plants typically don't have cogeneration, just given you don't have the return on investment is not typically seen. Um, with cogeneration, you also need biogas conditioning required ahead of your cogen system. So this is a fun graphic of a cogeneration system at a treatment plant up in Seattle. As you can see, you have your digester in the middle, you have your methane going to your engine and your generator to produce renewable electricity. You've got your heat exchanger loop and the hot sludge going back into your digester. And like I mentioned a couple slides ago, you do need to condition your biogas prior to a cogen unit. This varies widely between plants based on the type of sludge that you have, but potentially you'll need to remove H2S, siloxanes, and water vapor. So another key parameter to anaerobic digestion is digester pressure. The digester pressure needs to be measured in the digester and in digester gas or biogas piping everywhere on the plant. Um, the digesters they will be designed with a dome or a cover with a specific pressure rating. Um, and if you've been to a wastewater treatment plant, you've probably seen these valves, prong-looking things seen on the lower right corner of your screen. Those are pressure relief valves. Those are set to release if your pressure in your digester builds or if vacuum conditions occur. We also typically see emergency relief vents installed for additional safety. These will be released before your pressure rating on your digester cover is exceeded. The pressure, like I mentioned earlier, the pressure in your gas line is also, it's very important for that to be monitored at all times so you can see how your system's operating and if you're getting close to one of your valves going off or if your pressure is too low. With pressure and the biogas, you'll typically have flares. So a flare is another emergency gas release that's used at plants. You can either have an open or a closed flare based on the air quality regulations in your area. The flare is typically used whenever your gas production exceeds gas required for the boiler or the cogeneration system, or when your gas pressure does not meet the requirements for the boiler or cogen system. So typically your boiler or cogen system will have a minimum operating pressure for it to be efficient in either utilizing biogas or producing different forms of electricity. So in the case where maybe your pressure is too low, you'll send your biogas to the flare, the pressure will build up, and then you can send it back to your cogen unit, or vice versa. If you are producing way too much gas and you need somewhere for it to go, the flare will turn on and your biogas will be released that way. So anaerobic digestion, pros and cons. Um, Pros, obviously, you can produce biogas, which can be used um, to create energy or used to supplement other types of gas in your plant. We can handle a variety of different wastes. So we can handle fats, oils, and grease, other food wastes, reduced odors for anaerobic digestion because the tanks are closed. And then you can have, based on the classification of your sludge, you could use your digested sludge as a fertilizer or land application. And then also you do have a higher sludge volume reduction and volatile solids reduction in anaerobic digestion. Some cons to anaerobic digestion are given all of the moving pieces and parts of the system, you do have higher operating and maintenance costs. There's also a risk of methane emission from the biogas and then the potential for explosion, which will be mitigated by the different safety measures taken with the biogas system, including the pressure relief valves, but there is potential if not monitored properly. So there are a couple of technologies that can improve digestion or anaerobic digestion. The first being thermal hydrolysis. So thermal hydrolysis is a pre-treatment to anaerobic digestion. Basically, it goes on the sludge upstream of your anaerobic digester, and you heat the sludge to a high temperature and it under pressure. So this basically breaks down your microorganism cell walls. Um, the liquid that's produced is easier to treat than the regular sludge, and also it's easier to pump. And with this, you typically see a higher volatile solids reduction and a reduced energy required in the digestion process because your sludge is already at a higher temperature. Another technology that we touched on a little bit to improve anaerobic digestion is called co-digestion. So that would be when you're adding in fats, oils, and grease, other solid waste, food waste, other organic waste to the process. This can stimulate biological activity and improve your biogas production. All right. And then do we have any questions?
We do, yes. So we've got a couple. The first one was from Caleb back on aerobic digestion, and his question, which I misunderstood at first, was should we be adding LLMO, uh, which actually means live liquid microorganisms and not the lower layered microbial organization that I thought. So should we be adding liquid live microorganisms to aerobic systems?
That is a great question. Um, I don't have the answer to that right now, but let me look into it and I can get back to you, Caleb.
Yeah, and my initial take was, and this is kind of both for aerobic and anaerobic systems, is for the seeding of
Mhm.
your digesters when you first start up. So normally you will have like present in wastewater, you will have microbial organisms that are going to be digesting this stuff anyway. So it's kind of the organism colonies that you have in an activated uh, sludge system are going to be similar to the colonies in an aerobic system because both are, aerated. On startup, I think you can add liquid microorganisms if you need to get a jump start or if it's really cold where you are and you need to your microbial communities aren't super active and you need to give them like a little boost. I think that would be it. And then for
Mhm.
and then Hannah, please feel free to correct me if I'm
Oh,
wrong, but for for anaerobic systems, you'll normally use seed sludge from like an
mhm.
existing anaerobic digester. So if you've got another wastewater treatment plant down the street, or maybe if you're nearby to a dairy, so uh, dairy farms will also use anaerobic digesters to manage all of their cow manure, so they're also another common place to get seed sludge from.
Yes, that's a great answer, Emily. Yeah, that makes a lot of sense. Oftentimes it's seen at the beginning of the process when you're starting up the plant.
Yes. Second question from Sean is, what are the typical filters used for biogas? I know carbon is one of them.
Yes, it depends a little bit on the type of biogas. I know there are specific treatment technologies for siloxanes and H2S. And then I know, at least to get water out of your system, you typically have drip traps or oh, what are they called? The
Like like a condenser.
yes, yeah. Yeah, so that's an important pre-treatment step, but yes, definitely very specific to um, the type of constituent that you're removing, but
Yeah,
yeah,
and I think another point is it also depends on how far you're upgrading your
yes.
biogas. So this presentation only covers, biogas for boilers or cogeneration on site. But if you're going to be upgrading to RNG or renewable natural gas, there's a whole nother uh, chemical or not chemical, but processes that are required, including like pressure swing absorption to get rid of like the CO2 contents um, to separate out CO2 and methane to kind of upgrade it to
Mhm.
that RNG standard.
Yes.
Yeah, let us know if that answers your question. And then, okay, great, Sean. And then last one is from Mark. So, how do you optimize the balance between hydraulic retention time and organic loading rate to maximum biogas production while minimizing the risk of digester upset? And that is a great question, Mark. Always, always the issue. Hannah, do you have?
Yeah, I know that one's a tough one. It's pretty site specific as well. Just making sure that um, you're consistently monitoring and I it's yeah, I'm having a hard time answering this one. It's pretty site specific, but I don't know, Emily, if you have any.
Um, yeah, I was gonna say it's almost sort of trial and error. So your digester will have sort of its, design criteria, uh, loading points. And mm, there could be ways that you could like intensify the process to kind of maybe increase your hydraulic retention or increase your organic loading rate without upsetting your digester. So that could be for aerobic digestion, like Hannah said, using more oxygen.
Mhm.
For anaerobic digesters, really maintaining your pH.
Yes.
So anaerobic digestion is a little bit harder because you have a couple rate limiting steps. I think the last step of methanogenesis is rate limiting, meaning it
Mhm.
takes the longest. Also, that initial part of, I think the hydrolysis breaking things down into smaller is rate limiting. So, maintaining pH, alkalinity, making sure that you're not acidifying your digester,
Mhm.
because uh, and I was just thinking, if, back to your slide where it kind of shows all those steps. If you form too
Yeah.
much, yeah, if you form too many volatile fatty acids and you don't give it enough time to progress, that's kind of how you end up acidifying your digester, and then your colonies kind of die off. So uh, it is site specific. If that,
Mhm.
but those are some of the considerations that you have to look out for.
Yes.
Any, okay, great. Okay, any other questions? Digesters are pretty fun and complicated. Okay, I think that might be it.
Okay, that's great. Yeah, and if more questions come up, I think we're going to take a little bit of a break right now. But if you have more questions, please feel free to add them to the Q&A or in the chat, and we can address them when we get back from our break as well.
Yes, I think we are still ahead of schedule. That was the end of the digester section, right?
Yes, yeah.
Okay, great. So we have another 5-minute break coming up. So we will return at 9:55.
All right, great.
Okay, everyone, we are reaching the end of our 5-minute break. Before we get going into this kind of last half of the presentation, Hannah had reminded me to mention about the PDHs. So um, this training, even though we're going a little fast, is still eligible for 4 PDH hours. There were a couple questions in the chat about providing email addresses. So if you registered for the webinar using your email address, you will have that recorded. However, it's common for groups of people to watch the presentation together. And if you did not register and join the webinar with your email address, please put that in the chat for us to make sure that we can get PDHs for everyone. And we will be mailing out a self-reporting form in the next couple of days. And before we move on, do we have any other questions?
I'm not seeing any in the Q&A.
All righty. Let's
Thanks,
cue up.
Emily.
Yeah, of course. Okay, next we're going to go over dewatering. So, dewatering. Dewatered solids is kind of one of these final solids handling steps. So we've been going through, we've been concentrating the solids, we've been doing a little bit of pathogen reduction if we have an aerobic or anaerobic digester. We're also concentrating the solids, kind of reducing that putrefaction potential, pathogen reduction as well in the digesters because your community will be out competing other organisms that are in sewage sludge. And now we get to dewatering. So we're just continuing to dry and concentrate the solids over time. So the dewatered solids that you get are, we refer to it as cake. Your typical range of cake is going to be anywhere from 10 to 40% solids, depending on your feed sludge parameters in your upstream processes, and then also your type of dewatering process. So the dewatering processes that we'll be going over are centrifuges, a belt press, a filter press, and a screw press, or screw press, excuse me. Okay. Why should we dewater sludge? Similar to thickening, it has a lot of the same benefits. So you reduce your volume of your sludge, which reduces your storage and transportation costs. It also eliminates liquids for pre-landfill disposal, if that is your final disposal route. If you have a dryer, again, incinerators aren't applicable for Arizona, but in another state, if you have an incinerator, or if you're using a dryer for biosolids pathogen reduction, it reduces your fuel requirements because, again, you have less water to heat up, and it improves your composting efficiency. So through dewatering, you can concentrate up to 5 times your inlet sludge volume, and this all leads to lower capital costs and operational costs. So the first technology we will look at is centrifuges. So centrifuges are normally only used for WAS, or that waste activated sludge, prior to anaerobic digesters. They're not suitable for primary sludges coming out of the primary clarifier because there may be abrasive material in the primary sludge, which can ruin the internals of your centrifuge since they spin at very fast RPMs. And the separation process behind centrifuge is that you're using centrifugal force to separate out solids, where the solids go to the outside and water is maintained on the inside. And these also have an internal auger that pushes out the sludge. So sludge goes in, spins around, is concentrated, and sort of is pushed out by this auger. Similar to all of our thickening processes, we have a lot of similar operational parameters, including polymer dosing and age, your rotational speed and RPM, your effluent wear height. So that will kind of be your controlling parameter for solids and liquids coming out of your centrifuge, your solids feed rate, and also the temperature at which it operates. Some operational measurements that you need to take on a daily basis are your mixing and dosage and your age rates, the solids feed rate going in, the total solids of your feed, sludge, and cake, and the total solids or total suspended solids coming out in the centrage to close that mass balance. So there are an expected range of performance for centrifuges depending on your sludge type and your polymer dosing. A couple things to note out of here is just that primary undigested, which again is not recommended, will have different feed inlets, solids concentration or WAS undigested, and the range of polymers can vary. So this will be site specific, but we are all assuming you could all achieve sort of similar cake solids percentage in that like 10 to 40% range. Some pros of centrifuges is that they have overall a lower O&M cost and better performance than belt presses. They are designed to handle high loadings and they have pretty stable solids recovery operations with polymer addition. So once you get your system dialed in, you can produce a pretty consistent product. They also have a small footprint, like per the capacity of solids throughput that they can handle. And then under stable conditions, they have minimal operator input required. Again, it will take a little bit to figure out the exact operations of your system, but once you get it figured out, it's pretty stable. And they also have a very low exposure of operators to pathogens, H2S, and odors. Some cons with centrifuges is that because they are spinning around pretty fast, they have a high power consumption. And they also are pretty noisy when they're in operation. And they can have, because you have a lot of very fast moving parts, um, uh, again, a lot of experience can be required to kind of figure out your operational optimization, sort of getting your RPMs right and your polymer dosing correct. Oftentimes, the pedestals that centrifuges are placed on will require structural design due to the high rotational speeds. We want to make sure that your centrifuge doesn't go anywhere. And they also do require long startup and shutdown procedures to kind of allow for these gradual speed changes. Next up, we have a belt press. So a belt press, similar to a filter press that we saw in dewatering, it uses a belt with extra steps. So you're having your belt is semi-permeable, still separating solids from the liquid. Pressure is applied at various points along the belt via rollers and gravity. So in this first upper part, you're having the gravity drainage zone. Solids fall down, and then they are pressed against a series of rollers to provide extra pressure for separating out the liquids from the solids. And again, we have a series of belt wash areas to kind of help clean those pores and keep the belts open and clean. So some operational parameters include your sludge type, if you're using primary sludge versus secondary sludge. Your belt operations might be a little different, might be a little faster, a little bit slower. It also could change the type of sludge conditioning, polymers and coagulants and flocculants that you are adding. Belt pressure and tension is also going to be an operational parameter that you can control to get your targeted cake percent. Similarly, belt speed, so the faster it goes, you might get a little more throughput, but you also might get less solid separation, so balancing those two. And then sort of this hydraulic solids loading rate of your belt. So some operational measurements that you'll need to take. Again, polymer mixing and dosage, your solids feed flow rates, and the total percent solids in your feed sludge and your cake, and then also in your filtrate to make sure that your mass balance is working out and you're getting the expected performance that you require. And then this table shows a very similar comparison for primary sludge, WAS, with varying levels of polymer. One thing to note is the polymer dosage for the belt press on here is lower than the polymer feed that was required by a centrifuge. And you can get higher cake solids percent as well. And it can handle a range of feed solids from raw primary sludge to um, commingled digested sludges. So some pros of a belt press include low staffing requirements, pretty simple maintenance. It's a series of, it's a belt and roller. It has a faster startup and shutdown than a centrifuge because less complicated mechanical parts and you're not going as fast. And it's also less noisy than a centrifuge. Some cons is that more operator involvement is required if your solids feed is going to be varied. Centrifuges can handle a variety of feeds and get a fairly consistent product. Belt presses are a little more finicky. So, and if you have a higher fog in your sludge, that can bind to the belt, which will require more operational cleaning. And then routine belt washing is required at the end of each shift. And then odors can be present and require ventilation if you're going to use a belt press. Next up is the filter press. So there are a couple different kinds of filter presses, but they have a very commonality where sludge is sort of pumped into these hollow spaces and press in between plates, and the plates fill between each cycle. There's normally a cloth bag that will separate that will contain the solids, and so that filter bag is permeable to water. And so the plates are squeezed together and you create a cake. So the three common types of filter presses are plate and frame. So you've got a flat solid plate, a hollow press cloth, and these hollows form between each plate for cleaning and removal. At the end, these all come apart and you have to separate the cake from each of these filters. The next one is a recessed plate. So with the plate and frame, you're fed through a top corner and it sort of trickles down to fill the plate inside. With a recessed plate, you're fed through a sort of central hole distribution, and this gives you better solids distribution and better pressure distribution throughout, so you can get sort of more even performance across all of your filter presses. And then there is a diaphragm squeeze, and this is sort of the fanciest version of the filter press. And this one employs a secondary pressing process that requires special cloths and plates. So with the diaphragm squeeze, you are introducing sort of an extra squeezing step at the end, and it requires pressing cloths that are a little more structurally stable to resist those higher pressures. So some operational parameters for the filter press. Obviously includes your filter press type. Different types will have different performances. The number of plates. So if you have more plates in your plate and frame filter press, you can have a higher overall solids loading, just as you have more hollows to fill. Your press cycle time, there is a diminishing rate of return after a certain cycle time at a given pressure. You want to do some experiments and find out sort of what your optimal cycle time is, because too short means you still have pretty wet cake, but too long means you're, pressing for no added benefit. Similarly, the pressure of the feed coming in and then the pressure of the press cycle will also impact your cake form or performance. Again, polymer dosage and age. Then also, if you're going to be adding lime stabilization, your feed rate is also another operational parameter that you can control, and also the amount of lime that you're adding. Uh, so some operational measurements, like with all of the other processes that we've seen, your filtrate, total solids, TSS, your feed cake, your feed sludge and cake, total solids. So the chemical dosing required has some nuance to it. So if you're going to use ferric or lime for conditioning or odor control, it could end up accounting for a very high percent of the solids, up to 15 to 40% of the cake solids that you are um, forming. So this table here on the right um, will increase. So if you're dosing with lime for tertiary sludge, for example, you'll get a higher cake percent than, if you're just using primary and WAS without lime dosing. But one thing is that you're adding a solid into your solids. And so it's part of this 55% that you're getting out is going to be the lime that you're adding. And similarly with aluminum. So filter press. Some of the pros include you can achieve a high solids concentration, which again will reduce your storage, handling, and disposal costs. Uh, while these things are dewatering, your press phase can last anywhere from 1 to 3 hours. Minimal operator attention is required. Then you can go do something else while this is pressing. Um, the cake concentration can be fairly independent of feed concentration. Again, your cake concentration will sort of be determined by how long you're pressing for, the pressure that you're pressing at. Um, Lime dosing will disinfect the final product, so that can kind of help you get a little closer to some Class B classifications. Uh, and you can dose polymer as opposed to lime and ferric for conditioning as well. So you have a little more operational flexibility with the chemicals that you use. And then higher cake solids improves ease of downstream operations. Some cons to a filter plus is that they are pretty complex mechanically, so more moving parts, more spare parts to keep on hand, be a higher capital cost. And it requires a fairly large footprint and a special support structure as well. And because these are batch process operations, after each batch is done, there is maintenance required on that filter cloth. So you have to prepare the cloth, you have to clean it, you have to remove the cake that was formed, and that can be pretty time intensive. And then during this cake release, there is the potential for exposure to odors, H2S, and ammonia, which is why you will be dosing lime or ferric to kind of control these hazards. And as I mentioned earlier, if you're going to use ferric and lime for conditioning, it can result in a pretty substantial fraction of your cake solids. Next technology we're going to talk about is a screw press. So a screw press has an internal auger similar to a centrifuge, but much lower speeds, and the drum itself is not rotating. So sludge is fed into an auger, also known as a screw. The space between the auger threads become progressively smaller and smaller and smaller. So the idea here is that as the space becomes smaller, you are increasing the pressure. So you're going to be having the same volume of solids coming through here. And then hopefully, as this volume gets smaller, you're going to be removing more and more water. One item to note is that this hopper must be cleaned at the end of every shift. Some operational parameters for a screw press include the feed rate to auger volume. So your auger has a set volume. You can change the rotational speed, and these are sort of the main physical parameters that are going to determine your maximum amount of throughput, and then also the cake solid percent that you get at the ends. And then, as with everything else, polymer dosing as well to increase solid separation. Operational measurements that need to be taken, total percent solids of the cake and the filtrate, and also the sludge coming in. Your auger rotational speed, you'll need to see what your rotational speed is supposed to be, then also your cake production volume. So here we have a table that sort of shows the operations of a screw press with different sludges and at different polymer dosing. So as you can see, sort of towards the bottom, we have a slightly lower solids percent going in. We can still have an over 90% solids capture rate, but it does require, more polymer dosing than, say, if you're going to be using it for primary sludge that already has a higher percent cake solids, which does make sense. So some pros and cons of a screw press. Some pros are that they are less susceptible to clogging than filter-based technologies like the plate press or the even the belt press, because there's no pores to be clogged. Because of the low speeds and the lower pressure, there's less noise than with the centrifuge. There's no need to replace filter cloths. There's really no consumables in the screw press process. And luckily, so the polymer overdose will not clog screens or really affect dewatering. So if you get too much polymer in your solids, it can inhibit the dewatering process. A screw press is pretty straightforward, mechanical, and you don't really have that much sensitivity with that. Some cons is that it can achieve not as high of a solids percent in your cake as filter technologies, and it has a slower processing time. And because they are a sort of set volume processing limit, your capacity and throughput limitations could require additional units for higher capex. So this might not necessarily be as intensive as a process. So in summary, we have this table that shows the performance of different dewatering technologies for primary sludge, activated sludge, and the sort of mixed digester sludge. And these are the relative ranges of percent solids that you can expect out. So we see variability on the type of sludge that you have and variability on the type of technology that you're going to use. We have things ranging from, again, 15% to 40%, a little over 40% for primary sludge in a filter press. So some overall maintenance that is required, sort of regardless of your dewatering system, is all of these require polymer pumps, and that requires, pump maintenance, motor maintenance. Any motor that you have on your equipment will need to be maintained. Depending on the technology that you have, there's always going to be routine cleaning of screens, belts, hoppers, conveyors, polymer pump lines, etc. Polymer, you will always need a make-down system to mix the polymer, let it age correctly. So that will always require system maintenance and cleaning. And again, follow all of your manufacturer recommendations for your specific technology. Do we have any questions?
Not at the moment in the Q&A, but we can give, or in the chat, we can give others a minute or two. Yeah, not seeing
Okay.
anything come in, but I think
All right.
we can move forward. Thanks.
Yeah, great. Thank you. Okay. We're approaching the end of our solids processing processes, so we're gonna go over drying next. So, why do we dry? Up until this point, the main focus of our solids processing technologies have really been to essentially just concentrate the solids percent. Depending, if you have a digester, there can be some biological transformation, which can assist with vector reduction and putrefaction reduction potential. Uh, but barring all of that, sludge drying is really where you start to see a reduction in pathogens and vector attraction. Um, and that's also uh, gives you a reduction in freight and storage costs of the sludge. So we're just reducing the water even more through this process. And then most importantly, sort of for biosolids is you generate a stabilized product that can be stocked, handled, transported, um, either for further processing to Class A or for, sort of final disposal. Uh, so the technologies that we will be covering are lagoons, drying beds, and thermal drying. So I believe it was Tim had some questions on the facultative lagoon. So let us know if we answer. Um, First up is lagoons. So um, lagoons can be aerated, aerobic stabilized lagoons help prevent odors. So you get odors when you kind of get these anoxic conditions. If your sludge is, sort of settling out, forming a layer, letting things go anaerobic or anoxic. So you want to make sure that the depth of your beds are relatively shallow. The supernatant is decanted and recycled back to the headworks of the wastewater treatment plant. Um, since these are fairly passive, your cycle time can vary from several months to several years. Uh, your final total solids coming out of this can be 25 to 30%. Um, a couple of items to note with the odors is that uh, lagoons are not suitable for undigested sludges, lime sludges, or high strength supernatants, just because of that odor potential. And again, so it's a similar microbial process as aerobic digestion, more or less without mixing. The picture in this slide is just relying on gas transfer between the water and liquid phase at atmosphere. Uh, but if you throw on, an aerator, you can make this more of a facultative lagoon. So some operational parameters are your solids loading rate. Depending on your throughput, so if you have a higher temperature or if it's windier, sort of where you are, you can have variation in loading rate that is measured in BOD per volume per day. Your thickness of your sludge layer is another operational parameter. You don't want to let this get too thick and go anoxic depending on the depth of your lagoon. Drying time, unless you're going to be helping with the stirring or anything, this can take months to years. The leachate that comes out as well as the supernatant has to go back to the wastewater treatment plant. The normal operational parameter for lagoons is that they will be in use for 18 months and then rested for 6 months, sort of cleaned out and then reused again. Some operational measurements are your sludge feed and flow and your solids percent, the supernatants, solids and flow rate back to the wastewater treatment plant, your dried solids TS as well. And then also, because this is a sort of batch lagoon process, your retention time, your SRT, your HRT is another operational measurement. So some pros and cons to lagoons. They're very low capital cost. If you have a lot of lands, you dig a shallow hole and let your sludge sit, and it's very low capital cost. It requires minimal involvement. It requires the least amount of skill and experience to operate a lagoon. Organic matter is further stabilized. Again, you're just given it a little more time to break down, and there is no chemical consumption with this other. One of the cons is that it does require a large amount of land. So if you are space limited or CapEx limited. This might not be the best option. You can get potential odor and vector issues with that sludge blanket buildup. There is potential for groundwater contamination, so you will need to make sure that your leachate system is operating correctly. And it's really not suitable for wet and cold environments. And further processing of sludge is required for biosolids application. Next up is sort of a conventional drying bed. So drying beds operate where several layers of sand and gravel are used for drainage, and they can achieve up to 50 to 70% solids because of this additional drainage layer. The leachate must be collected and treated. It's assumed with the leachate that there is no pathogen treatment that has been achieved. So it must go back to the headworks or to another treatment system. And then solids must be turned over to expedite drying. So if you can get, a little backhoe or a cat in here to kind of turn these solids over, that will expedite your drying. Similarly to lagoons, the solids that you get out of drying beds are not fit for immediate reuse, and they must be further stabilized by some other sort of treatment, either composting or lime, some other stabilization process. A fun variation on solar drying beds, which I heard are used in Arizona, are solar drying beds. So solar drying beds are essentially a sort of, say, greenhouse-esque type of building that is used to dry solids. So you cover the solids, you ventilate them. Um, this is good when you have a lot of solar sun, or maybe if you live in a little, colder climate, maybe a little bit wetter. Solid drying is achieved by the solar radiation and aeration. So inside this building, you will have some fans that are sort of actively providing airflow. And the coolest thing about this is that it has sort of this automated rake system that will turn over your sludge for you, which reduces sort of operator involvement, having to go out there with heavy equipment, and it decreases your drying time, so you can achieve a final solids percent of around 60%. And as you can see, this roller will sort of push all of these dehydrated sludges down to one end of the building for easy removal. Another added benefit of solar drying beds is that it can provide additional long-term storage for solid storage, and it also provides a higher pathogen removal than conventional drying beds. So
And
some
I'm really
common,
sorry.
yep, yep,
We've got a couple questions in the chat, so I figured
great.
they have to do with, well, the first one has to do with lagoons, so before you get too far.
Okay,
Um,
lagoon.
all right. So Tony asked, what is the appropriate disposal method for dried sludge disposal from lagoons?
So
Yeah.
we'll get into this a little later in the presentation for lagoon solids. If you're transforming them into biosolids, they need to be further stabilized, either can be chemically stabilized or they can undergo a further heat process, so it's sort of more in a dryer. So these are all the passive drying processes, but there are other processes that use like a heating medium that we'll get into in a couple of slides. But uh, yeah, and then I think as far as direct disposal of those, you would have to check your local regulations if you can dispose of it via landfill without uh, additional pathogen reduction. I'm not sure on that.
Yeah, I would agree and assume probably direct bury at a landfill, or you could further process it at, like a composting facility or something like that.
Yeah.
Cool. And then we have one other question. Steve asked suggestions for testing for polymer residual in belt press effluent.
Polymer residual and belts press effluents. Um, I
I think,
think,
oh, go ahead.
no, go ahead, Hannah.
No, I think that would, I think monitoring your percent or the amount of polymer that you're putting into the belt press is definitely really important because it doesn't necessarily get destroyed. So the polymer comes out with your sludge.
Yeah, and I'm just trying to think. I mean, uh, for regular solids testing, I mean, there's a way to measure like like the inorganic ash, if you put it in a muffle furnace. And I'm wondering if you could do a similar mass balance on your, sort of
Hmm.
your effluents and then also your cake solids percent, and then also your feed going in so you could get like a relative idea of where your polymer is going.
Hmm. Yeah, that's a good idea.
Yeah.
Great.
But I think also if you overdose polymer, I think you can sort of see it
Yeah.
um, in the solids. Just like your solids won't really be, compressing or dewatering. So that's kind of an indication that you might be over applying chemicals.
Nice. Cool. Thank you. And then I think Jamie in the chat said solar drying is good for Yuma, Arizona. So yes, definitely. Arizona is a
All
good
right.
good place for it.
Good. Good to hear. Yeah, I know. This is when I was putting together this presentation. This is the first time I had seen this. So, so really neat technology. Glad to hear it's being used where you have, so much sun.
Yeah. Great. Well, thanks, Emily.
Great.
That was the last question. So.
Great. Thank you, Hannah.
Mhm.
Okay. Okay. So going back to drying beds. So some common operational parameters that they all have, your sludge loading rate, the thickness of your sludge layer, how often you're turning it over, the drying time. So conventional beds, not the lagoons. So just for the drying bed here, it can be 10 to 15 days to dewater and then several more weeks to sort of dry because it is a more um, passive process and you're relying on, ambient conditions to further dry that solids to your target cake solids percent. Solar beds, the entire process takes about 30 days to dewater and dry. Um, and then specifically with the solar beds, sort of the temperature inside that you keep because you're getting that greenhouse effect, and then also the airflow rates of your solar drying bed will impact your drying time and performance. Some operational measurements. Always got to take that feed sludge flow and total solids percent, your dried solids total solids percent, and then also the drying time. If you have a fairly consistent uh, sludge flow characteristics to your drying beds, your drying time will be pretty consistent. So you can kind of set it and forget it until it's time to go and, turn it over or and test to see if you can, if you've reached your targeted concentration to remove the solids. Some pros for drying beds. Uh, Again, lowest capital cost when land is readily available, minimal operator involvement. It has low energy consumption. It relies on solar energy. Even with the solar drying beds, I think really the only power usage are going to be some fans that are turning to provide airflow and then sort of that rake that's moving back and forth. Minimal chemical consumption. Also, perhaps no chemical consumption if you're not dosing for Lyme or ferric for odors and stabilization. Um, and drying beds provide a good CapEx ratio for low to medium size communities. Some cons to drying beds are that large amounts of land are required, so not necessarily good, if you're in the middle of the city. It does require further stabilization of the sludge to prevent septic conditions before you go for long-term storage. Sludge removal can be pretty labor intensive, not suitable for wet and cold environments unless they're covered. Again, that leachate must be collected and treated, and it does have limited pathogen removal because you are just relying sort of on ambient temperature conditions. Okay, going on to this next step, which goes back to that question about solids disposal from, lagoons, is heat treatment. So we have a series of dryers. So you can have standalone systems, such as like a belt dryer or a batch dryer. You can also retrofit them onto dewatering processes. If you don't want to have, a lagoon necessarily, you can put dryers on the back ends of centrifuges, a belt press, screw press, a plate press. And the benefits of heat treatment are that you get that pathogen and odor reduction. So the heat will destroy microbes that are left over, and it also will further remove biodegradable carbon, which just reduces that odor potential and vector pathogen reduction. So first up is thermal drying. Thermal drying is combined drying and pathogen reduction is achieved, and there are three options. So you have direct, indirect, and infrared, and we'll go through each of these. But before that, this is an example picture of a dryer. So you've got wet sludge that comes in. It will go, in this instance, it's going through sort of a belt, so it can be a continuous process. You get dried sludge out. And then for all thermal dryers, you always have a heating medium. And the way that this heating medium comes into contact with the solids is how we differentiate between direct and indirect. In this instance, you have a heater that is heating and dehumidifying air, which is important. We don't want to send hot, wet air to solids because we don't want to introduce more water into the system. So hot air comes into contact with the wet sludge. We get the hot, wet air out. The water is removed via condensate, and then the whole cycle continues again. But this is the general idea behind thermal drying. So your final solids percent can be controlled by time and temperature. So higher temperature, you're going to get a higher TS percent. Longer time at the same temperature, you will also get a higher TS percent than a shorter processing time. You can get over 90% total solids in your biosolids out of a dryer. And again, as I mentioned, there are three types of dryers: convection, which is direct, conduction, which is indirect, and then infrared. There are three stages of heating. You have sort of this warm-up stage where you're needing to overcome the sort of energy to kind of separate that water from the liquid phase, to the vapor phase. Once you've kind of reached that activation energy, you can be at a constant drying rate. You reach sort of your critical moisture, and then you can have a falling drying rate as well. So as your water percent in your solids decreases, you can feed less energy to the system to continue drying your solids. So direct dryers, for direct dryers, solids are in direct contact with your drying medium. Usually this is hot air. Some operational parameters for direct dryers include the temperature of the air, the speed of the air. This is all just sort of heat and energy transfer. So if you have hotter air and you have faster air, you're going to be taking off more water at a higher rate. The contact surface area as well. So we would like to have a high surface area versus a low surface area. Higher surface area means that there's more opportunities for water to come out of the liquid phase into the vapor phase. The humidity of the air, again, if you're sending in wet air, you're going to remove less water from the biosolids, but if you send in dry air, you're going to get more water removed. A couple types of direct dryers include a bio dryer. This is pretty interesting. This can use bacteria to generate heat, which can achieve pathogen reduction, but also kind of lower your electricity cost. And then there's also a Fenton dryer where you can really customize sort of your final solids percent. You have a lot of operational flexibility with that. Next is an indirect dryer. So as the name suggests, your heating medium is in indirect contact with your biosolids. So this can normally be like a hot liquid, similar to a radiator, where you're having heat exchange across a chamber. So you have a wall that separates the sludge from the heating medium. In this picture here, you have your indirect heat source. This is going to be your contact area. So whatever the surface area of here is, that'll impact your drying rates, your throughput, and then also sort of the final temperature of your biosolids coming out. There are a couple configurations. One is a paddle or a screw dryer. So that is the one shown up in the top here. So rotating drum and paddles turning the sludge promotes uniform drying and efficient heat transfer. So you're not getting, crusty solids at like the edge and wet solids in the middle. So similar to a drying bed, kind of creating uniformity of solids moisture and drying potential throughout is really great. Another indirect dryer configuration is a belt dryer. So you have a circuitous belt path that allows a lot of surface area for contact. And it also provides sufficient time for dehydration. Um, uh, and it's seen here, so for the belt dryer, you can use a range of uh, heating mediums for power, for fuel, including biomass gas or steam, or any other fossil fuel products. Another indirect sludge dryer configuration is a thin film dryer. So the thin film dryer is really maximizing the surface area that you're exposing the biosolids to. So you might have a total lower volume of solids in your dryer, but you're getting a higher rate of heat transfer. So it kind of balances out. The idea behind this is that a thin film of sludge is applied to the outside of a rotating drum. The rotating drum moves around, gives it adequate time to contact with your heating medium, and then is removed after you've reached your solids retention time. This cross section shows better what is going on inside. So you've got you've got a series of blades that are rotating in here. The inside of this tube is hollow, so you're really just doing the heat exchange process in this very last outer shell. So you have your biosolids that are applied. You have this heating surface, and then your heating fluid is applied in between in this very most outer shell here. So we're getting induction heating across. Spaces above the biosolids allow for the released moisture to be captured and vented out. Last of the thermal drying is infrared. So infrared uses IR or infrared electromagnetic waves to heat and dry sludge. This is similar to how a microwave heats food. Microwaves are, I believe, above the visible light spectrum, so they have a lot of energy. Infrared is below the visible light spectrum. It's just another way to heat and dry sludge. And because we are using sort of electromagnetism, some of the operational parameters are going to be the exact wavelength that you use. The intensity, so intensity is kind of like a bright light bulb versus a dim light bulb. And then also your sludge throughput, so how much solids retention time you're giving your infrared dryer. Some pros and cons of thermal drying is that you can produce Class A biosolids. So for Class A, you have to have that pathogen reduction and also achieve at least a 90% biosolids. Um, you also have the preservation of a lot of fertilization compounds in the biosolids because you're not exposing them to like really, really high extreme temperatures that would degrade a lot of those sort of beneficial soil amendments. There are no requirements for special equipment for land application because you are producing Class A biosolids. Um, and then the sludge is suitable for incineration, not in Arizona, but in other states, or landfilling. Some cons. Solids can catch fire. So just like you have sort of explosion potential with anaerobic digesters because you're making, methane, you are heating up solids that are already kind of dry to a higher, drier temperature. Um, so solids can catch fire if they're overheated. So attention is required for these to make sure that you are not over processing your solids and over drying them to the point where they will combust. They also have a higher energy cost, so about 3,000 kilojoules is required to transform 1 kilogram of water from liquid to vapor. Over a long time and over a lot of solids, that can add up to a fairly high energy bill. Um, Higher CapEx is required than lagoons or drying beds. Again, lagoons, drying beds, you dig a hole in the ground, probably with a tractor that you have around. These are more complicated machines and also requires skilled operator training. And while all of these do produce Class A biosolids, the sale that you get from that Class A biosolids may or may not offset the higher CapEx, OpEx. So this is something that will need to be looked at before deciding to adopt one of these. So some maintenance that's required. All heating equipment is going to require maintenance for, filaments, making sure that you're not, burning out any of your metal parts, routine cleaning of screens, belt, hoppers, conveyors, etc., just like with any of our other drying. There is special maintenance required for the infrared dryers because we are using specific, types of light bulbs to kind of create this infrared radiation. Again, follow all manufacturer recommendations. And dryers, we do prefer that they are operated with supervision, again, because of that fire risk. One kind of final note on solids handling is PFAS and microplastics destruction. So with the latest regulations coming out, and sort of we have a higher public awareness of PFAS and microplastics in biosolids, we wanted to talk a little bit about some reduction potentials. So PFAS are per and polyfluoral alkyl substances. Microplastics are defined as anything being from a plastic piece that is anywhere from 5 millimeters to 1 micrometer. So that's a pretty large variation. Some PFAS and microplastics removal destruction technology include pyrolysis, gasification, or smoldering. These are all they're all different technologies, but they operate under the same idea that you are heating up your biosolids to a high temperature, normally in the absence of oxygen, to really break down those chemical structures. Also, per PFAS, there are other high temp processes like supercritical water and plasma. Those are pretty complicated to operate. And again, incineration, not for Arizona, but you would use a fluidized bed reactor for that. Okay, any questions?
Don't have any in the Q&A right now. Give people a minute to check. I was also thinking we are moving pretty quickly. I was wondering if we wanted to do maybe a little 5-minute break before our last couple of sections.
Yeah, that sounds good to me.
Okay.
Okay, so come back at 10:55.
Great.
Unless
See
we have,
everyone in
okay.
a little bit.
Yeah. Okay, hi everyone. We're reaching the end of our final 5-minute break. We did get a question about PFAS over the break, so I just want to go back and kind of talk about it again a little more. Um, so PFAS are a class of substances. They are characterized by sort of a long hydrocarbon chain and then a fluorine compound on the end. And the fluorine bond is pretty hard to break, which means that, so PFAS are also known as forever chemicals if you've heard them in the news. They are, they're used in Teflon for anti-stick. They're used in raincoats for sort of water repelling. They're used in fast food containers to make sure that, your food doesn't stick and your fries come out. Uh, they're also used in fire suppression systems, flame retardants, stain-resistant carpet as well. They have a really wide use of applications, and there are several states, I think, including Maine, that have banned biosolids application for agricultural use because of a concern of PFAS in the biosolids, sort of like long-term accumulation in the soils or transfer from the soils, to food and then to people. So that's why, depending on the regulations in your area or your targets end user, if you have a client that's looking to buy your biosolids, uh, they may bring up PFAS, so you may need to consider, further PFAS reduction technologies at the end. Okay, we are hitting the home stretch here. So we have biosolids, we have dry biosolids. What do we do now? Um, okay, so what do we do with all these solids? So if your downstream processes have not already produced Class A or Class B biosolids, we will need to do stabilization. I also can go, I'm going to talk a little bit about the regulatory framework. So sampling required, and then landfill versus Class A and Class B uses. And then we'll also go over a little bit about agronomic loading rates. And that's sort of it's a calculation of your nutrient loading for land management. Um, and then in this section, we're going to be getting into some of the nitty gritty of the Class A versus Class B treatments. So first up is lime stabilization. So why do we use lime stabilization? It reduces pathogens, it eliminates odors and odor-causing compounds. It provides sort of long-term inhibition and reduction of putrefaction potential. And it stabilizes non-classified biosolids. So if you don't already have Class A or Class B, this is a good way to stabilize them. How does lime stabilization work? So you're reducing the volatile organic content of your solids when you add lime. Also, the addition of lime reduces and prohibits microbial activity because your lime is very alkaline, so you're raising it above their preferred pH conditions in which they want to live. Additionally, lime can provide beneficial reuse for land reclamation. So if your final disposal site is a acid mine spoils, the alkaline content in the lime can help sort of buffer and neutralize the acidity of your mine spoils. And so what is lime stabilization? We add lime, which is a very alkaline or basic substance. We can use it to achieve Class A and Class B biosolids. For Class A, you want the pH to be 12 or above, and you want it to be at a temperature of 52 degrees C for 12 hours. So for Class B, you want it to be at a pH of 12 or above for only 2 hours. So to no surprise, Class A requires a longer processing time, and it has a temperature component to really meet that pathogen reduction value that we're looking for Class A. Some sampling required. So you need sampling pre and post stabilization. So before you apply the lime, you need to take samples. After you apply the lime and let it sit, you need to take samples. And this is for pathogen monitoring. You'll see how many pathogens you have in your pathogen cultures you have in your uh, raw sample, and then after your stabilized sample, you also need to take the pH of your solids, and that will determine if you have the correct lime dosage. Temperature, if you're going for class A, you'll need to monitor the temperature sort of throughout, and then also the processing time. Some pros for lime stabilization is that it's consistent with EPA's 503 biosolids rule. So it's accepted by the EPA. You have an end product that is ready to be sold. It's a very simple technology, minimal skill is required. Um, a small land area is required to let the biosolids sit for lime stabilization. You can have pretty flexible operation, fast startup and shutdown. You throw in lime, you mix it around, you let it sit. And it also helps prevent ammonia off-gassing from non-treated solids. So if you have maybe a little bit of a simpler wastewater treatment plant that hasn't gone through some of these biological treatment processes, lime can kind of help prevent that ammonia off-gassing for less treated solids. The con is that it may not be suitable for all soil applications because it is going to be more alkaline. Um, and again, similar with some of those dewatering technologies, the volume of your stabilized solids could be anywhere from 15 to 50% higher than other stabilization technologies because we are adding in a powdered lime substance, which is a solid. There is potential for odor and dust generation during this process. Uh, and there is also a pathogen regrowth potential if the pH drops below 9.5 during storage. So you want to make sure that your um, dosage of lime and your processing time is going to be adequate to make sure that our pH doesn't drop later on. And because we are adding lime, your final biosolids product will have a lower nitrogen and phosphorus content due to the chemical reactions that are involved with the lime. You've got volatilization of nitrogen, and you'll form a calcium phosphorus compound when you add the lime as well. Some solids handling regulations, as we've seen before, EPA Part 503 biosolids Class A and B, they require you to submit a biosolids annual report. For the state of Arizona, we have a couple of these House rules and legislatures, and you are required to apply for a biosolids general permit. One note about Part 503. So 503 is a self-implementing rule. So you need to meet these rules and requirements even if a permit has not been issued. And it's sort of the idea is, just because you don't necessarily know it's the law doesn't mean that you're not liable if you don't meet these requirements. And so action can be taken against a party who doesn't meet Part 503 requirements. So again, biosolids are regulated. We just want to make sure that we are meeting all those regulatory requirements. Okay, some sampling required for end uses include if it's going to be land applied or if you're going to do another surface disposal, such as at a landfill. You have required biosolids reporting. We've got class 1 sludge management facilities, and these include facilities that are 1 MGD or higher, or if they serve a population of 10,000 plus people. So these sites will be subject to these regulations. Okay, solids handling regulations. This is a lot of detail. The main things to note here are that sampling analysis is required for pathogens. So the pathogens that we had talked about, coliform, viruses, helminth. There are additional requirements for sewage sludge for metals, so arsenic, cadmium, copper, lead, nickel, mercury, selenium, and zinc. Um, and then also, There are pollutant limits for non-domestic septage if you have a combination. And there are also additional regulations under the AZPDES Biosolids General Permit. Okay, so for Arizona specifically, you have specific pollutant limits for several metals and different monthly and maximum or ceiling concentrations, as well as um, varying monitoring frequency. So depending on the amount of biosolids that you are producing, your monitoring frequency with which you have to test for all of these constituents changes. So for smaller facilities on the low end, anywhere from 0 to 290 metric tons once per year. And for the really large facilities up to over 15,000 metric tons, you need to test once every 30 days. So we're going to talk about pathogen reduction for Class A and Class B. And before we get into all of those details, I wanted to go over some definitions. So depending on the pathogen that you are looking at, there are different essentially measuring units. So we've got most probable number, colony forming units, CFUs, plaque forming units, and further throughout, we've got fecal coliform, enteroviruses, Helminth ova, and Salmonella. So for Class B, we have three alternatives. Alternative one is you measure fecal coliform density, and that's measured in MPN or CFU. Alternative two is, as Hannah had said earlier, if your biosolids are treated via a process to significantly reduce pathogens as determined by the EPA. And then alternative three is treated via a process to significantly reduce pathogens as determined by your Arizona permitting authority. So they may have slightly expanded or slightly different processes that they consider for reducing pathogens. So there are ways to go about this for both the state and federal level. So what does it mean to significantly reduce pathogens? Well, we have sort of five main ways. We have aerobic digestion, anaerobic digestion, air drying, composting, and lime stabilization. Um, the the exact rules have a lot more language and several fairly complicated formulas with which you use to sort of calculate your MCRT to make sure that you're hitting your, temperature over those number of days. I didn't want to include that here. I think it would just be a little overwhelming. My my hope for this is just to kind of give a broad overview of these processes so that you can get a relative idea of, the time and the temperatures at which these operate. So starting with aerobic digestion, you'll see that you have a longer MCRT than anaerobic digestion. Anaerobic digestion requires a higher temperature, which means that you have, less days. Air drying has a a very long time. Again, because it's a lot more passive and you're just sort of relying on solar radiation. Composting is pretty short, so you've got shorter shorter number of days. You kind of like this peak hour at a 55 degrees C to eliminate a lot of pathogens. And then we've already talked about lines of stabilization for Class B. All right, Class A, there are 6 options for your biosolids alternatives. And each of these alternatives has a different parameter that they are measuring or a different pathogen that they are measuring. And they have different sort of biosolids parameters that are used. So for instance, if we take a look at alternative one is measuring for fecal coliform or salmonella. And this one is dependent on your total percent solids. So how long your time and temperature has to be held for is dependent on the total solids going in. Alternative two is also measuring fecal coliform and salmonella. Um, this is more sort of pH and pH dependent and time dependent, and also has a different solids threshold concentration. So your solids need to be at least 50% to use alternative two. Alternative three is a little less prescriptive. It measures enteric viruses and Helminth ova, uh, and it just says that before or after pathogen treatment, you need to meet these thresholds, but it doesn't really tell you how you need to get there. Alternative four, again, is measuring for all four of these pathogens. And this is just saying at the time of use, sale, or application, your biosolid needs to hit these pathogen concentrations. Alternative five says that you're measuring for fecal coliform and salmonella or salmonella, and you need to have this PFRP, which is Class B biosolids treatment, or sorry, Class A biosolids treatment. Alternative six is anything that's already been through a Class B pathogen reduction process and Class B site restriction requirements is eligible for Class A. Okay, so how do we get Class A processes? So what are these PFRPs processes to further reduce pathogens? There are 7, as you can see, that are included in EPA's 503 rule. The first one is composting. The second is heat drying, heat treatment, thermophilic aerobic digestion, which goes back to the presentation earlier by Hannah. We have beta ray irradiation, which is pretty interesting, gamma ray irradiation, or pasteurization. So, and again, these all have different sort of time and temperature requirements that you need to hit operationally. And there are also fairly complicated formulas that are used to determine if you hit these, temperatures during your residence time. So briefly, so composting, if it's within vessel or it's an aerated pile, you need less stays because we are assuming that we're getting more microbial activation in the composting process if we're actively aerating it and kind of mixing it more. The retention time is longer if it's just going to be a windrow with 5 turnings. Also at 55 degrees C, so pretty warm. Heat drying, as we had talked about, there is direct or indirect for your solids coming out. They need to have a moisture content of less than 10%, a final sludge processing temperature that is above 80 degrees C, and a gas wet bulb temperature of at or above 80 degrees C. And this gas wet bulb temperature is used to measure sort of the moisture content in your vapor that's being removed from the biosolids. Heat treatment, number 3. So if you have a liquid sludge from your processes, heat that sludge up for 30 minutes at 180 degrees C, and you will have met Class A processes. Thermophilic aerobic digestion, also a liquid sludge, longer time, lower temperature. So it's all of these processes are sort of this balance between time and temp to kind of kill off these microbes. Beta ray irradiation, this uses an accelerator. I have not heard of this before, so that was news to me. You need to have an intensity radiation of 1 megarad at 20 degrees C. Similarly for gamma ray irradiation, this is pretty interesting. This uses radiation from unstable isotopes, normally cobalt or CE, it's not selenium. I'll have to go back and look. I don't remember. but you have a gamma ray radiation also of at 1 megarad at 20 degrees C. And then lastly, we have pasteurization. This also might be used for a liquid sludge or a drier sludge, but 30 minutes at 70 degrees C. So you have a lot of options to get to Class A. And if you have questions on what it says, Part 503 has a lot of language. Okay. I guess before we go on, do we have any questions on Class A, Class B, cesium? Thank you, Dennis. Appreciate that. I'm not as familiar with the upper end of the periodic table anymore.
Not seeing anything in the Q&A or the chat right now.
Okay. All right. Well, then we can continue. If you do have any questions, just let us know. Okay, so sort of one of the final pieces of putting all of this together is something called an agronomic loading rate. So we started this presentation several hours ago talking about why do we want to use biosolids. They give us water, they give us nutrients. So plants will uptake nutrients from the soil, including nitrogen, phosphorus, and potassium. Different species have different uptake rates that they are approved for. So one of the main things that we are looking at here is that we don't want to overload the soils with these nutrients, particularly like nitrates. So if you use, you see this issue a lot with inorganic fertilizers in heavily agricultural areas where you can get groundwater contamination, surface water runoff contamination. Just from these nutrients leaching out of the soil and going into different water sources because the plants have not taken them up yet. And because of this, the amount of biosolids that is applied to a particular piece of land is limited to sort of help prevent, we're probably mainly worried about long-term groundwater pollution, but other surface water runoffs as well. And the biosolids application is measured in tons per acre. So this was the simplest example of the nitrogen cycle that I could find. And really what I want to point out here is, so we're going to be kind of in this example here of fertilizers that are applied to soil. There's a very complex microbial interaction in the soils and in the roots of the plants themselves that are taking up nitrogen or fixing nitrogen. If it's going to the plants that are being harvested, that's great. Anything that is not fixed or taken up can exit out as runoff or groundwater. If you have a full night cycle, you'll also give nitrogen to the atmosphere, but that's not where the majority of your nitrogen is going to be going. And so ideally, the nitrogen and other constituents that we are applying to land and biosolids is being taken up by the plants, but there is a limit. Grasses that grow really fast, you can apply more biosolids to. Alfalfa is a really common one. Slower growing plants, maybe if you have nut trees or if you have citrus trees, they could have like a lower growing rate and a lower agronomic loading rate that you can apply. And excess nitrogen can cause surface water and groundwater pollution. Okay, and so we're kind of going back to full circle to this web application available through ADEQ. So one of the reasons that you want to take a look at the amount of biosolids that you're applying to a piece of land is to make sure that you're not going over your specified agronomic loading rate for organic nitrogen, ammonium nitrogen, and nitrates. And this will provide a nitrogen mass balance of your current and previous applications. So nitrogen in biosolids, they kind of they're taken up over a series of years, depending on what you're growing there. So this is sort of an additive process. So if you apply biosolids year one, you'll use a certain amount, but you'll have a certain amount left over And then if you apply biosolids again, year 2, you'll have your new biosolids nutrient loading plus whatever is left over. So it's important to kind of keep track of it through the whole life cycle process. And here are references to the specific rules and legislation where you can find the specific requirements. Okay, any questions?
I haven't seen any come into the chat yet, but yes, please let us know if you have any.
Great. Okay, and then Hannah, I think we're heading the final 2 sections for you, so I can stop sharing if you want to take over.
Perfect.
Okay, I'll stop sharing.
All right. Okay. Are you able to see my screen?
Yes.
All right, great. Thank you, Emily. So going into the last 2 sections of our presentation, we wanted to give a little brief overview of the different types of pumps that you can use for sludge applications. Um, First off, starting with centrifugal pumps. So I think we've probably all seen these in the plants. They're pretty common. For solids, we would typically use these for activated sludge applications. They would be solids handling or non-clog centrifugal pumps. They come with a recessed impeller or I guess the second type would be a recessed impeller or a chopper pump, and these would typically be for more high solids, so your primary sludge, fats, oils, and grease, or digester mixing. So the chopper pumps would typically be if you have a fog station at your plant, that's what you would see there. It kind of chops things up a little bit more going into the digesters. So another very common type of pump that we often see in sludge applications are progressive cavity pumps. These are a type of positive displacement pump that is used for thickened sludge in highly viscous applications because of the stator. These pumps are generally self-priming, but there is potential wear of the rotors and the stators in those pumps. And you can see this is the stator. It's a long piece of metal that pushes the fluid into the pipe. So another common type of pump is a rotary lobe pump. The rotary lobe pump is another positive displacement pump. Basically, as the video shows, you've got 2 rotating lobes that push the fluid forward into a pipe. Typical applications for rotary lobe pumps are waste activated sludge, thickened sludge, and digested sludge, typically up to about 4% solids. And another common type of pump is a peristaltic pump. This is another type of positive displacement pump. You may see a theme. Positive displacement pumps are really good for solids application. The peristaltic pumps are typically known as hose pumps because they have a hose that fluid runs through that's moved by shoes or rollers, as you can see in this image down below. Typical applications for this, again, are waste activated sludge, thickened sludge, and digested sludge. So for these types of pumps, pretty typical pump maintenance, oil changes if your pump has oil, lubrication of bearings and joints, inspection of wear parts, replacement of casings, and then adequate clearance is required for stator replacement for the progressive cavity pumps because for some of the pump models, you need to pull the stator out from the end. The pump maintenance would typically be provided by the manufacturer on a suggested frequency. So you can look at your data sheets and pump specs for more detailed information on each of the different types of pumps. And just to summarize, centrifugal pumps applications, activated sludge, primary sludge, fog, digester mixing. Think of them more for high flow applications, progressive cavity and peristaltic pumps for low flow applications, thickened sludge, sludge transfer, and then rotary lobe is pretty flexible, WAS, thickened sludge, digested sludge, low to high flow. So I know that was a really quick overview of the different types of pumps that we typically see in sludge applications, but wanted to pause to see if anyone had any specific questions.
Doesn't look like we have any questions yet.
Okay, cool. Sounds good. And then the last small section that we wanted to go over was about building classification and ventilation. So the classification that applies most closely to sludge treatment is NFPA 820, which is the National Fire Protection Agency. Within their set of codes, they've got a section dedicated to wastewater and sludge treatment. This regulation calls for the protection against fire and explosion hazards at wastewater treatment plants. It goes through each different location and function of sludge treatment process that could be present at a wastewater treatment plant. So, for example, digestion, solids dewatering, solids thickening, anywhere that you might have biogas. It dictates the required ventilation and equipment classifications for the room. So if you're processing sludge in one room and potentially have biogas, you could need a higher rate of ventilation in that room to keep the atmosphere safe for humans to be in and working. And additionally, with the equipment classifications, you may need a different classification on your motor, like a NEMA 4X, for example, if you're around a flare. So we have a couple different classifications under NFPA 820. The first being unclassified, which means that you would not need additional ventilation in your building or specialized motors or equipment. Class 1 Div 2 tightens that requirement a little bit. So you may need additional ventilation, but it might not be the maximum amount, or you might need different specifications on your motors. And then class 1 div 1 is the most restrictive and requires a high rate of ventilation and explosion proof motors. So on the next sheet, this is an example of a diagram that you can see from the NFPA 820 regulation. So this is for an anaerobic digester. So the solid gray that you can see around the anaerobic digester and in the sludge gas piping might be by a control building. You can see where you would need to classify all of your equipment as Division 1. And then the striped area is a 5-foot envelope around the Div 1 area, and that requires, like I was mentioning, not as high of caution, but still some caution. And then the white area is unclassified. So these types of figures are provided in NFPA 820 for each of the different proposed sludge treatment processes. So if you have access to that, it's a really great tool for if you need to replace pumps or motors, or even if you're just working in the area, making sure that the ventilation is properly running and adequate to make sure that you're safe. And with that, we have come to the end. We're a little bit early, but if you have any other questions, please feel free to put them in the Q&A or the chat, and we would love for you to fill out this feedback QR code. If you don't mind, we'd really appreciate any feedback on areas where you'd like to see more information or areas that you thought maybe we went a little overkill on. We'd love the feedback to improve for our next round of presentation.
Yeah, great. Thank you, Hannah. Then one final comment I just want to reiterate is on the PDHs. We will be mailing out a self-reporting form that you will return to ADEQ. There's an email that you can contact. And if you have any questions, please feel free to send Hannah and I an email. A recording of this presentation will be available on the ADEQ website within a week or so after this presentation is over. And I think that was kind of all the housekeeping requirements.
Yeah, thank you all. We really appreciate you taking the time to attend.
Okay, great. Thank you.